2,000 years before the light bulb, before the telegraph, before the first wire ever carried a current through a laboratory in the modern world, someone in the ancient land between the Tigris and the Euphrates rivers built a device that could generate electricity. It was not large, it was not dramatic. It was a simple clay jar, roughly the size of a human hand, sealed with asphalt, fitted with a copper cylinder and an iron rod, and when filled with an acidic solution, it produced voltage. Measurable, undeniable, real voltage. This is not speculation, this is not myth. This is an archaeological fact that has baffled scientists, historians, and engineers for nearly a century. The question is not whether these devices existed. They did. The question is what they were used for. Were they instruments of ancient science, tools for gilding sacred objects in gold, devices for delivering therapeutic shocks to the human body, or evidence of something far more extraordinary, something that challenges everything we believe about the timeline of human technological progress? This is the story of the Baghdad Batteries and what they may reveal about the lost knowledge of the ancient world. Please let us know in the comments where you are watching this history video and what time you are watching it. And be sure to subscribe to the channel for future videos. It begins, as so many great archaeological stories do, with an accident. Not a planned excavation carried out by a prestigious university. Not a carefully documented dig funded by a national museum. It begins with construction workers, shovels, and the simple act of digging into the earth near a small village on the outskirts of Baghdad, Iraq, sometime in the early 1930s. The workers were not looking for artifacts. They were not looking for history. They were doing what workers do. They were moving earth, laying foundations, preparing the ground for the modern world to be built on top of the ancient one. But the ground had secrets. What they unearthed that day was a collection of clay jars, small and unremarkable at first glance, buried in the ruins of what appeared to be a Parthian-era settlement dating back roughly 2,000 years. The jars were sent to the National Museum of Iraq in Baghdad, where they sat among thousands of other artifacts, catalogued but not yet understood, waiting for someone to look at them with the right kind of curiosity. That someone arrived in 1938. His name was Wilhelm König, and he was a German painter and archaeologist who had been serving as the director of the National Museum of Iraq. König was not a specialist in electrochemistry. He was not a physicist. He was an artist and a student of antiquity who had come to Iraq during a period when European scholars were deeply involved in the study and excavation of Mesopotamian civilizations. But König had something that many of his contemporaries did not possess. He had the ability to look at an object and see beyond its surface. He had the willingness to ask a question that others might have dismissed as absurd. When König examined the clay jars that had been pulled from the earth near Baghdad, he noticed something unusual. Each jar was approximately 5 to 6 inches tall, with a wide mouth that had been sealed with an asphalt plug. Protruding through the asphalt was a copper cylinder, and inside the copper cylinder was an iron rod. The iron rod did not touch the copper cylinder directly. It was separated from it, insulated, suspended within the copper tube. The asphalt seal held everything in place. And the interior of the jar showed signs of having once contained a liquid, traces of which suggested an acidic substance, perhaps vinegar or wine. König recognized the configuration. It was not the configuration of a storage vessel. It was not the configuration of a ritual object, at least not any ritual object he had ever seen. It was, in its essential structure, a galvanic cell. A battery. A device capable of converting chemical energy into electrical energy through the interaction of two dissimilar metals in an electrolytic solution. The implications were staggering. If König was correct, then someone in the ancient Parthian Empire, in a time when the Romans were still building their republic, when the Han dynasty ruled China, when the classical world was still centuries away from its peak, had constructed a working electrochemical device. Electricity, the force that would not be formally studied until the experiments of Luigi Galvani and Alessandro Volta in the late 1700s and early 1800s, had been harnessed, however crudely, 2 millennia earlier. König published his findings in 1940 in a paper that proposed these artifacts were indeed ancient batteries. His paper did not cause the immediate sensation one might expect. The world was at war. Europe was consumed by conflict. Academic journals were not reaching their usual audiences, and the idea of ancient electricity was so far outside the mainstream of archaeological thought that many who did read König's work dismissed it as fanciful overinterpretation. Surely, they said, there must be a simpler explanation. Surely these jars were storage vessels or scroll containers or objects with some mundane religious function. Surely the similarity to a battery was coincidental. But König was not the last person to examine these artifacts, and as the decades passed, the question he had raised refused to go away. To understand why the Baghdad Batteries are so controversial and why they matter, we must first understand the world from which they came. We must travel back 2,000 years to the land of Mesopotamia, to the empire of the Parthians, and to the ancient cradle of civilization itself, Mesopotamia. The name itself means the land between the rivers, a reference to the Tigris and the Euphrates, two great waterways that flow from the mountains of modern-day Turkey southward through Iraq and into the Persian Gulf. This narrow strip of fertile land, watered by seasonal floods and enriched by millennia of deposited silt, was the birthplace of human civilization as we know it. It was here, in the marshes and plains of southern Iraq, that the Sumerians built the first cities more than 5,000 years ago. It was here that writing was invented, that mathematics was formalized, that astronomy became a science, that law was codified, that agriculture was systematized, and that the great ziggurats rose toward the heavens as monuments to the ambition of the human mind. Mesopotamia was not one civilization. It was a succession of civilizations, each building upon the ruins and the knowledge of the one before. After the Sumerians came the Akkadians. After the Akkadians came the Babylonians. After the Babylonians came the Assyrians. After the Assyrians came the Neo-Babylonians, who built the Hanging Gardens and watched as their king Nebuchadnezzar conquered Jerusalem. And after the Neo-Babylonians came the Persians, who swept in from the east under Cyrus the Great and absorbed Mesopotamia into the largest empire the world had ever seen. The Persians, in turn, were conquered by Alexander the Great in the 4th century before the Common Era. Alexander died young, and his empire fractured into successor states. Mesopotamia fell under the control of the Seleucid Empire, a Hellenistic dynasty founded by one of Alexander's generals. The Seleucids brought Greek culture, Greek language, and Greek science to the ancient lands of the East, creating a fusion of traditions that would shape the region for centuries. But the Seleucids could not hold their vast territories forever. From the northeast, from the harsh steppes and mountains of what is now Iran, came a people known as the Parthians. Originally a semi-nomadic Iranian tribe, the Parthians rose to power under their leader Arsaces in the 3rd century before the Common Era, founding a dynasty that would endure for nearly 500 years. At its height, the Parthian Empire stretched from the Euphrates River in the west to the borders of India in the east. It controlled the vital Silk Road trade routes that connected the Roman world to China. It was one of the great powers of the ancient world, a rival to Rome itself, famous for its mounted archers, its decentralized system of vassal kings, and its remarkable ability to absorb and synthesize the cultures of the peoples it ruled. The Parthian Empire was not a monoculture. It was a vast, multilingual, multi-ethnic tapestry of peoples and traditions. Within its borders lived Persians, Greeks, Babylonians, Arameans, Jews, and dozens of other groups, each contributing their own knowledge, their own technologies, their own ways of understanding the world. The Parthians were not merely warriors. They were administrators of one of the most culturally diverse empires in human history. They inherited the astronomical knowledge of the Babylonians, the philosophical traditions of the Greeks, the metallurgical skills of the Persians, and the commercial networks of every trading civilization that had ever operated along the routes between East and West. It is within this context, this rich and complex cultural environment, that the Baghdad Batteries were created. They were not the product of a primitive society. They were the product of a civilization that had access to thousands of years of accumulated knowledge, a civilization that stood at the crossroads of the world's great intellectual traditions. And that fact, more than any single experiment or analysis, is what makes the batteries so plausible and so provocative. Let us now examine the artifacts themselves in greater detail, because the physical evidence is the foundation upon which every theory must be built. The objects commonly referred to as the Baghdad Batteries are a collection of roughly a dozen clay jars discovered at Qujat Rabu, a site near Baghdad that dates to the Parthian period, roughly from 250 years before the Common Era to 224 years of the Common Era. The jars vary slightly in size and condition, but they share a common set of features that distinguish them from ordinary pottery. Each jar is made of yellowish clay, a common material in Mesopotamian pottery production. The jars are roughly 5 to 6 inches in height, with a diameter of approximately 3 inches. They have a narrow mouth, wider than a scroll jar but narrower than a typical storage vessel. The mouth of each jar was sealed with a plug of bitumen, a naturally occurring asphalt-like substance that has been used in Mesopotamia for waterproofing and sealing since prehistoric times. Bitumen seeps naturally from the ground in many parts of Iraq, and its use in construction, boat building, and artifact making is well documented throughout Mesopotamian history. Through the bitumen plug, a copper cylinder protrudes. The cylinder is made of a thin sheet of copper that has been rolled into a tube and soldered along its seam with a lead tin alloy. The copper cylinder is approximately 3 to 4 inches long and roughly 1 inch in diameter. Inside the copper cylinder sits an iron rod, approximately the same length as the cylinder but slightly thinner. The iron rod is held in place by the bitumen plug and does not make direct contact with the copper cylinder. At the bottom of the copper cylinder, a copper disc or cap is sometimes present, further separating the iron rod from the copper. This arrangement, two dissimilar metals separated by an insulating material and enclosed in a vessel capable of holding a liquid, is the essential structure of a galvanic cell. When an electrolyte, any acidic or alkaline solution that can conduct ions, is placed in the jar, a chemical reaction occurs between the iron and the copper. The iron, being more reactive, begins to oxidize, releasing electrons. These electrons flow through an external circuit if one is connected to the copper, which is less reactive and serves as the cathode. This flow of electrons is electricity. It is the same fundamental principle that powers every battery ever made, from Volta's original pile in 1800 to the lithium-ion cells in modern devices. The voltage produced by a single Baghdad battery is small, typically estimated at between 0.5 volt and 2 volts, depending on the electrolyte used. This is not enough to power a motor or illuminate a modern light bulb, but it is electricity nonetheless. And if multiple jars were connected in series, as batteries are connected in modern devices, the voltage would increase proportionally. 10 jars connected in series could produce 5 to 20 volts. 20 jars could produce more. The current would remain low, limited by the small surface area of the electrodes and the resistance of the electrolyte, but the potential for useful electrical work would exist. Some researchers have also noted that the copper cylinders show evidence of corrosion consistent with exposure to an acidic solution. The interior surfaces of the copper tubes exhibit a patina that is different from the corrosion one would expect from simple exposure to air or water over 2,000 years. This corrosion pattern is more consistent with electrochemical activity, with the kind of chemical reaction that occurs when a metal is immersed in an electrolyte and subjected to an electric current. This is not conclusive proof that the jars were used as batteries, but it is a detail that supports the hypothesis. The iron rods, too, show signs of unusual corrosion. In some specimens, the iron has been almost completely consumed, eaten away by oxidation in a manner that suggests prolonged exposure to a reactive chemical environment. If the jars had been empty, or if they had contained only water or a neutral substance, the iron would have corroded differently, more slowly, more evenly. The pattern of corrosion on the iron rods is consistent with their having served as the anode in an electrochemical reaction, the element that is gradually consumed as it gives up its electrons to the circuit. The bitumen seals are also significant. Bitumen is an excellent insulator. It does not conduct electricity. Its presence as the sealing material in these jars suggests that whoever built them understood, at least intuitively, the need to prevent direct contact between the two metals except through the liquid medium. If the copper and the iron were allowed to touch directly, the chemical reaction would still occur, but the electrons would flow directly from one metal to the other without passing through the electrolyte, and no useful current would be generated. The bitumen seal prevents this. It holds the metals in the correct spatial relationship to one another, separated but immersed in the same solution. This is not the kind of arrangement that occurs by accident. It is the kind of arrangement that occurs by design, but let us not get ahead of ourselves. Let us acknowledge the skepticism, because it is as important to this story as the evidence itself. The Baghdad batteries have been debated for decades, and not all scholars agree that they were batteries at all. The most common alternative explanation is that the jars were storage vessels, perhaps used to hold sacred scrolls, precious oils, or other valuable materials. Scroll jars are well known in the archaeology of the ancient Near East. The Dead Sea Scrolls, for example, were found in clay jars in the caves of Qumran, near the Dead Sea, dating to roughly the same period as the Baghdad Batteries. It is entirely possible, some scholars argue, that the Kujet Rabu jars served a similar purpose, and that the copper cylinders and iron rods were simply structural elements designed to protect and secure the contents of the jars. This argument has some merit, but it also has weaknesses. The Dead Sea Scroll jars do not contain copper cylinders or iron rods. Their design is quite different from the Baghdad artifacts. Moreover, the specific combination of two dissimilar metals inside a sealed container is not a feature of any known scroll jar or storage vessel from the ancient world. If the jars were meant for storage, the presence of the copper and iron elements is difficult to explain. Why go to the trouble of inserting a copper tube and an iron rod into a jar that is only meant to hold a scroll or a liquid? Why solder the copper seam with a lead tin alloy, a technique that requires specialized metallurgical knowledge? Why seal the entire assembly with bitumen in a way that isolates the metals from one another? These are not the features of a simple container. They are the features of a carefully engineered device. Another alternative explanation is that the jars were used in some kind of religious or magical ritual. The ancient world was full of objects that had no practical function, but were imbued with spiritual significance. Amulets, talismans, ritual vessels, and sacred implements are found at archaeological sites throughout Mesopotamia and the broader Near East. It is possible that the Baghdad jars were cult objects, perhaps used to hold a sacred liquid, or to represent some symbolic concept related to the dual nature of metals or the transformation of matter. This explanation is harder to evaluate because it is harder to disprove. We cannot interrogate the beliefs of people who lived 2,000 years ago. We cannot know with certainty what spiritual significance, if any, they attached to these objects, but the ritualistic explanation does not account for the electrochemical properties of the jars. If the jars were purely symbolic, why would they be constructed in a way that happens to produce electricity? Coincidence is always possible, but coincidence becomes less convincing when the coincidence is this specific and this functional. A third alternative explanation proposed by some archaeologists is that the jars were simply containers for transporting or storing liquids, and that the copper cylinders and iron rods were inserted later, perhaps as part of a repair or modification that had nothing to do with the original purpose of the vessels. According to this view, the apparent battery-like configuration is an artifact of the archaeological record, a misleading assemblage of unrelated components that were brought together by chance rather than by design. This explanation is weakened by the fact that multiple jars with the same configuration were found at the same site. If the copper and iron arrangement were the result of a random modification, we would expect to see it in one or two jars at most. The fact that it appears in a consistent pattern across multiple artifacts suggests standardization, which in turn suggests intentional manufacture. Someone was making these devices on purpose in quantity according to a specific design. That is not the behavior of someone repairing a broken jar. That is the behavior of someone producing a tool. There is also the question of context. The jars were found at a site that has been identified as a Parthian-era settlement, a place where people lived and worked. They were not found in a temple or a tomb, which might support a purely ritualistic interpretation. They were found in an area associated with daily life, with craft production, with the practical activities of a functioning community. This does not prove that they were batteries, but it does suggest that they were functional objects, tools of some kind, rather than purely ceremonial items. The debate continues to this day. No single piece of evidence has been sufficient to convince all scholars one way or the other. But the weight of the evidence, the specific combination of materials, the consistent design across multiple specimens, the electrochemical properties of the configuration, the corrosion patterns on the metals, and the context of the discovery points toward a conclusion that is as extraordinary as it is unsettling. These were not ordinary jars, they were devices. And they were designed to do something that we, in the modern world, did not think anyone knew how to do until 1800 years later. The story of the Baghdad Batteries might have remained a minor footnote in archaeological literature, a curiosity known only to specialists, if not for the work of a handful of researchers who decided to test König's hypothesis in the most direct way possible. They built replicas, and they turned them on. The first and most famous of these experiments was conducted by Willard F. M. Gray, an engineer at the General Electric High Voltage Laboratory in Pittsfield, Massachusetts, in 1940. Gray was not an archaeologist. He was an electrical engineer who had heard about König's discovery and was intrigued by the possibility that the ancient jars could function as batteries. He constructed a replica of the Baghdad Battery using the same materials described in König's paper: a clay jar, a copper cylinder, an iron rod, and a bitumen seal, and filled it with grape juice as a substitute for the vinegar or wine that might have been used as the original electrolyte. The result was immediate and unambiguous. The replica produced approximately half a volt of electricity. It was a small amount, barely enough to register on a sensitive meter, but it was real. The device worked. The ancient design, replicated with modern hands but ancient materials, generated an electric current. Gray's experiment was a landmark moment, not because it proved that the ancient Parthians used electricity, but because it proved that they could have. The design was functional. The materials were available. The principle was sound. Whatever the original purpose of the Baghdad batteries, they were capable of producing electricity. That fact was now beyond dispute. In the decades that followed, numerous other researchers replicated Gray's experiment with similar results. Some used vinegar as the electrolyte, some used lemon juice, some used a solution of copper sulfate, a substance that was known and used in the ancient world as a pigment and a mordant for dyes. In every case, the replicas produced voltage. The specific amount varied depending on the electrolyte, the quality of the metals, and the conditions of the experiment, but the range was consistently between half a volt and just under 2 volts per cell. One particularly notable series of experiments was conducted by Arne Eggebrecht, a German researcher working at the Romer and Pelagius Museum in Hildesheim, Germany, in the 1970s. Eggebrecht went beyond simply demonstrating that the Baghdad battery design could produce electricity. He attempted to show that it could be used for a specific practical purpose: electroplating. Electroplating is the process of using an electric current to deposit a thin layer of one metal onto the surface of another. In modern industry, electroplating is used to coat objects with gold, silver, chromium, nickel, and other metals, providing a decorative or protective finish. The process requires an electric current, an electrolyte solution containing dissolved metal ions, and 2 electrodes, one of which is the object to be plated. When current flows through the solution, metal ions are attracted to the cathode, the negatively charged electrode, and are deposited on its surface in a thin, even layer. Eggebrecht constructed a set of Baghdad battery replicas and connected them in series to increase the total voltage. He then used the combined output of the batteries to electroplate a small silver figurine with a thin layer of gold. The experiment was successful. The figurine was plated with gold, using nothing more than ancient materials and the electricity generated by clay jars filled with grape juice. This was a breakthrough result because it offered a plausible explanation for one of the enduring mysteries of ancient Mesopotamian metallurgy. Among the artifacts recovered from ancient sites in Iraq are numerous objects, particularly small statues, jewelry, and decorative items that appear to be coated with an extremely thin, extremely even layer of gold. The gold layer on these objects is too thin and too uniform to have been applied by the traditional methods of gold leafing or gilding, which involve hammering gold into thin sheets and pressing or gluing them onto a surface. Gold leaf, even at its thinnest, leaves visible seams and irregularities. The gold coating on some ancient Mesopotamian artifacts does not. It appears to have been applied by a process that deposited gold at the atomic level, evenly and seamlessly, onto the surface of the underlying metal. For decades, archaeologists and metallurgists had puzzled over how this was done. Various explanations had been proposed, including mercury gilding, a technique known in the ancient world that involves dissolving gold in mercury, applying the amalgam to a surface, and then heating the object to evaporate the mercury, leaving a thin gold layer behind. Mercury gilding is effective but toxic and leaves characteristic traces that are not always present on the Mesopotamian artifacts in question. Fire gilding, diffusion bonding, and other techniques had also been suggested, but none fully accounted for the quality and consistency of the gold coatings observed on certain ancient objects. Electroplating offered a compelling alternative. If the ancient Mesopotamians had access to simple battery technology, they could have used it to electroplate objects with gold, producing exactly the kind of thin, uniform coating that has been observed on archaeological specimens. The Baghdad Batteries in this interpretation were not curiosities or ritual objects. They were industrial tools, part of a metalworking technology that was lost when the civilizations that created it declined and fell. Eggebrecht's experiment was widely publicized and generated considerable excitement, both in the academic world and in the popular press. It seemed to answer the central question about the Baghdad Batteries. They were electroplating devices. The mystery was solved. As with so many things in archaeology, the answer was not as simple as it appeared. The electroplating hypothesis, despite its elegance and its experimental support, has faced significant criticism from scholars who argue that it raises as many questions as it answers. The first objection is practical. The voltage and current produced by the Baghdad batteries, even when connected in series, are extremely low. Electroplating even of very small objects requires a sustained current over a period of time. The Baghdad battery replicas produce current, but the current is weak and tends to diminish rapidly as the electrolyte becomes saturated with reaction products and the electrodes corrode. To electroplate an object of any significant size, dozens or even hundreds of batteries would need to be connected, and the electrolyte would need to be refreshed frequently. This is not impossible, but it is laborious, and it raises the question of whether electroplating with Baghdad batteries would have been practical on any meaningful scale. Modern electroplating operations use currents of several amperes and voltages of several volts, delivered by reliable, consistent power sources. The Baghdad batteries would have provided milliamperes at best, 1,000 times less current than a modern plating setup. At such low currents, electroplating would take hours or days to deposit even a microscopically thin layer of gold. It would work in principle, but it would be painfully slow and difficult to control. Whether ancient craftsmen would have found this method preferable to the faster and simpler techniques of mercury gilding or gold leafing is an open question. The second objection is archaeological. If the Baghdad batteries were used for electroplating, we would expect to find them in association with other metalworking tools and materials: crucibles, molds, hammers, anvils, gold wire, copper sulfate crystals, and the other paraphernalia of a metalworking workshop. We would also expect to find wires or connectors of some kind, devices for linking the batteries together and for connecting them to the objects being plated. But no such associated materials have been found at Qujat Rabu. The batteries were found in isolation, without any of the supporting infrastructure that an electroplating operation would require. This absence of associated materials is not necessarily fatal to the electroplating hypothesis. The site at Qujat Rabu has not been extensively excavated, and many artifacts may remain undiscovered. It is also possible that the batteries were found out of their original context, moved or scattered by later disturbance of the site. But the lack of supporting evidence is a weakness that proponents of the electroplating theory must acknowledge. The third objection is historical. If electroplating was practiced in the ancient world, it would represent a technological achievement of enormous significance. It would mean that ancient craftsmen understood, at least empirically, the principles of electrochemistry, the relationship between electric current and chemical reactions, the behavior of metal ions in solution, and the techniques for controlling the deposition of metal on a surface. This is a sophisticated body of knowledge. If it existed, we would expect to find references to it in the extensive written records of Mesopotamian civilization, which include thousands of cuneiform tablets documenting everything from astronomical observations to beer recipes to legal contracts. But there are no known references to electroplating, or to electricity, or to anything resembling a battery in any ancient Mesopotamian text. This silence in the written record is puzzling but not unprecedented. Many ancient technologies were trade secrets, closely guarded by the guilds and families that practiced them. The formula for Roman concrete, for example, was lost for centuries after the fall of the Roman Empire, despite being one of the most widely used building materials in the ancient world. The technique for producing Damascus steel, the legendary blades of the medieval Islamic world, was lost and has never been fully replicated. It is entirely possible that electroplating, if it was practiced, was a proprietary technique known only to a small number of craftsmen who did not commit their methods to writing. But the absence of written evidence remains a challenge. In a civilization that wrote everything down, from the movements of the planets to the price of barley, the complete absence of any reference to a technology as remarkable as electricity is difficult to explain. If not electroplating, then what? What else might the Baghdad batteries have been used for? One of the most intriguing alternative hypotheses is medical therapy. The use of electric shocks for medicinal purposes has a long history, and it may be far older than we think. In the ancient world, certain species of fish were known to deliver painful shocks to anyone who touched them. The electric catfish of the Nile, the torpedo ray of the Mediterranean, and the electric eel of South America all produce significant electrical discharges as a means of stunning prey or defending against predators. Ancient peoples were well aware of these creatures and their remarkable abilities. The ancient Egyptians depicted the electric catfish in tomb paintings dating back to the Old Kingdom, more than 4,000 years ago. The ancient Greeks and Romans wrote extensively about the torpedo ray, describing its ability to numb the limbs of fishermen who handled it. What is particularly interesting is that ancient physicians appear to have used these electric fish as therapeutic devices. Scribonius Largus, a Roman physician who lived in the 1st century of the Common Era, wrote a medical text called Compositions in which he recommended the torpedo ray as a treatment for headaches and gout. The patient was instructed to place the living torpedo ray on the affected area, where its electric discharge would numb the pain. This was, in essence, an early form of electrotherapy, the use of electrical stimulation to treat medical conditions. Electrotherapy is a legitimate and well-documented medical practice that continues to be used in the modern world. Transcutaneous electrical nerve stimulation, or TENS, is a common treatment for chronic pain that works by delivering small electrical currents to the affected area through electrodes placed on the skin. The electrical stimulation interferes with pain signals traveling along the nerves, providing temporary relief. Deep brain stimulation, another modern electrotherapy technique, uses implanted electrodes to deliver electrical pulses to specific areas of the brain and has been used to treat Parkinson's disease, depression, and other neurological conditions. If ancient physicians understood the therapeutic potential of electric fish, might they have sought to replicate the effect artificially? The Baghdad batteries, with their ability to produce a small but perceptible electric shock, could have served as a controlled, portable source of therapeutic electricity. Unlike a torpedo ray, which can only be used when alive and fresh, a battery can be stored, transported, and used at any time. It provides a consistent, repeatable stimulus that can be applied to specific areas of the body with precision. The voltage produced by a single Baghdad battery, roughly half a volt to 2 volts, is low, but it is within the range that can be felt by the human body, particularly when applied to sensitive areas such as the fingertips, the temples, or the soles of the feet. A tingling sensation, a mild shock, or a feeling of warmth would have been easily perceptible to an ancient patient, and in a world where the mechanisms of disease were poorly understood, such sensations could easily have been interpreted as evidence of healing power. If multiple batteries were connected together, the effect would be amplified. A bank of 10 batteries producing 1 volt each would deliver a 10-volt shock, which would be quite noticeable and potentially painful. This is within the range of the electric discharge produced by a torpedo ray, which can deliver shocks of up to 50 volts. A skilled practitioner, by varying the number of batteries and the duration of the application, could produce a range of effects from a gentle tingle to a sharp jolt, tailoring the treatment to the patient's condition and tolerance. The medical hypothesis is attractive because it explains several features of the Baghdad batteries that the electroplating hypothesis does not. It explains why the batteries were found in a residential area rather than a workshop. It explains why no metalworking tools or materials were found with them. It explains why the batteries are relatively small and portable, designed to be handled and applied to the body rather than integrated into a large industrial apparatus. And it explains why the technology might not have been recorded in written texts, since medical practitioners in the ancient world often guarded their methods as closely held secrets, passed down orally from master to apprentice rather than committed to writing. But the medical hypothesis also has weaknesses. There is no direct evidence that the Baghdad batteries were used for medical purposes. No ancient text from Mesopotamia describes the use of artificial electricity in medicine. No medical instruments have been found in association with the batteries, and the physical evidence of the artifacts themselves does not point specifically toward medical use any more than it points toward electroplating or any other application. There is yet another hypothesis that deserves consideration, one that is perhaps less dramatic than electroplating or medicine, but no less interesting. Some researchers have suggested that the Baghdad batteries were used for a purpose that is simple, practical, and entirely consistent with the technological capabilities of the ancient world. They may have been used for creating a religious or mystical experience. Imagine a temple in ancient Parthia. Imagine a priest standing before a sacred statue, a figure of gold and copper gleaming in the lamplight. The worshippers approach, their heads bowed, their hearts full of reverence. They reach out to touch the statue to receive the blessing of the god it represents. And when their fingers make contact with the metal surface, they feel a shock, a tingle, a jolt of invisible force passing from the divine image into their bodies. What would they think? What would they feel? In a world without any understanding of electricity, without any framework for explaining the invisible force that had just passed through their flesh, they would have only one explanation. The statue was alive. The god was present. The divine power was real, tangible, felt in the body and in the bones. This is not mere speculation. The use of hidden mechanisms to create the appearance of divine intervention is well documented in the ancient world. Hero of Alexandria, a Greek engineer who lived in the 1st century of the Common Era, designed a series of mechanical devices specifically intended for use in temples. His inventions included automatic doors that opened when a fire was lit on the altar, using the expansion of heated air to drive a pneumatic mechanism. He created holy water dispensers that released a measured amount of water when a coin was inserted, an ancient vending machine that would have seemed miraculous to the uninitiated. He designed wind-powered organs that produced music without any visible player, and steam-powered devices that rotated and whistled, creating the impression of supernatural activity. Hero was not unique. The Hellenistic world was full of engineer priests who used their knowledge of mechanics, pneumatics, and hydraulics to create theatrical effects in temples and sacred spaces. The goal was not deception exactly, but rather the creation of an experience that would inspire awe and reinforce belief. The technology was hidden, the effect was visible, and the worshipper, standing in the flickering light of an ancient temple, surrounded by the smell of incense and the sound of chanting, would have had every reason to believe that something supernatural was occurring. The Baghdad batteries could have served a similar purpose. Hidden beneath a statue or inside a wall, connected by thin wires to a metal surface that the worshippers would touch, the batteries could have delivered a mild electric shock that would have been interpreted as a divine sensation. The jolt would have been unexpected, mysterious, and impossible to explain by any natural means available to the ancient mind. It would have been proof, felt in the body, of the presence and power of the gods. This hypothesis is speculative, but it is not implausible. It accounts for the small size and portability of the batteries, which would need to be concealed within a larger structure. It accounts for the relatively low voltage, which would need to be startling but not dangerous. It accounts for the absence of metalworking tools and materials, since the batteries would not have been used for industrial purposes. And it is consistent with the well-documented practice of using hidden technology to create religious experiences in the ancient world. Of course, like every other hypothesis about the Baghdad batteries, this one lacks direct evidence. No temple has been found with batteries hidden inside its walls. No ancient text describes the use of electricity in religious rituals. The hypothesis is a possibility, not a proven fact. But it is a possibility that deserves to be considered alongside the others, because it reminds us that technology in the ancient world was not always used for the purposes that we, in the modern world, might expect. Let us step back for a moment and consider the broader implications of the Baghdad batteries, regardless of their specific purpose. Whether they were used for electroplating, medicine, religion, or something else entirely, their very existence raises a question that goes far beyond the archaeology of Mesopotamia. It raises a question about the nature of technological progress itself. We tend to think of technology as a linear progression, a steady march forward from simplicity to complexity, from ignorance to knowledge, from the primitive to the modern. We imagine our ancestors starting with stone tools and gradually, over thousands of years, working their way up to bronze, then iron, then steel, then electricity, then computers, each step building upon the last in an unbroken chain of advancement. This narrative is comforting because it places us at the top of the ladder, the most advanced civilization in human history, the inheritors of all the knowledge that has come before. But the Baghdad Batteries suggest that this narrative may be incomplete. They suggest that technological knowledge is not always cumulative, that it can be discovered, used, and then lost, sometimes for centuries or millennia, before being rediscovered by a later civilization that has no idea it is retracing steps that were taken long ago. This is not a radical idea. History is full of examples of technologies that were known in the ancient world and then forgotten. Roman concrete, as we have mentioned, was a material of extraordinary durability and versatility that was used throughout the Roman Empire for more than 500 years. The Pantheon in Rome, built in the 2nd century of the Common Era, has the largest unreinforced concrete dome in the world, and it has stood for nearly 2,000 years. Yet after the fall of Rome, the formula for Roman concrete was lost. Medieval builders could not replicate it. It was not until the 18th and 19th centuries that modern engineers began to develop concrete with comparable properties, and even today, researchers are still studying Roman concrete to understand its remarkable longevity. The Antikythera mechanism, discovered in a Roman-era shipwreck off the coast of the Greek island of Antikythera in 1901, is another example. This extraordinary device, dating to roughly the 2nd century before the Common Era, is a complex mechanical calculator that used a system of interlocking gears to predict the positions of the sun, moon, and planets, the dates of eclipses, and the timing of the Olympic Games. Nothing of comparable complexity would be built again for more than 1,000 years. The Antikythera mechanism was not part of a continuous tradition of mechanical engineering. It was a standalone achievement, a technological island, created by a civilization that had the knowledge to build it but apparently did not transmit that knowledge to its successors. Greek fire, the incendiary weapon used by the Byzantine Empire to devastating effect in naval warfare, is yet another example. The formula for Greek fire, which burned on water and could not be extinguished by conventional means, was a closely guarded state secret that died with the Byzantine Empire. Despite centuries of effort by historians and chemists, the exact composition of Greek fire has never been determined. The pattern is clear. Technologies can be invented, used, and then lost. Knowledge is fragile. It depends on the institutions and traditions that preserve and transmit it, and when those institutions collapse, whether through war, famine, plague, or cultural upheaval, the knowledge they carry can vanish as completely as if it had never existed. The Baghdad Batteries may be another example of this pattern. If the ancient Parthians or the Babylonians or the Persians or any of the other peoples of ancient Mesopotamia discovered the principles of electrochemistry, they may have used that knowledge for specific, limited purposes, electroplating, medicine, religious theater, or something we have not yet imagined. But when the civilizations that possessed this knowledge declined, when the Parthian Empire fell to the Sassanids in the 3rd century of the Common Era, when the trade routes shifted and the cities shrank and the craftsmen who knew the secrets of the batteries died without passing on their knowledge, the technology was lost. It lay buried in the earth for 2,000 years, waiting to be rediscovered by a world that had forgotten it had ever existed. The story of the Baghdad Batteries is also, in a way, a story about the limits of archaeology. Archaeology is a science of fragments. It works with what survives, with what the earth chooses to preserve, with the broken pottery and corroded metal and crumbling stone that remain after everything else has been destroyed by time. It is a science of inference, of deduction, of making educated guesses about the past based on incomplete evidence. And it is a science that is profoundly shaped by the assumptions and expectations of the people who practice it. When König first examined the Baghdad Batteries in 1938, he brought to the task a set of assumptions that were shaped by his own time and culture. He knew what a battery looked like because he lived in a world where batteries existed. He recognized the configuration of the Baghdad jars because he had a framework, a mental model, that allowed him to see the resemblance. If König had lived in a world without electricity, without any understanding of electrochemistry, would he have recognized the significance of the jars? Almost certainly not. He would have cataloged them as pottery, filed them in a drawer, and moved on. This raises an uncomfortable question. How many other ancient technologies have we failed to recognize because we do not have the framework to understand them? How many artifacts are sitting in museum drawers right now, dismissed as curiosities or misidentified as ritual objects, that are in fact the remnants of technologies we have not yet imagined? The Baghdad Batteries were discovered by accident and recognized by a stroke of intellectual luck. What else is out there, waiting to be seen by the right pair of eyes? This is not an argument for uncritical acceptance of every extraordinary claim about ancient technology. It is not an invitation to see flying machines in Egyptian hieroglyphs or nuclear reactors in Indian epics. It is a reminder that the past is deeper and more complex than we often assume, and that our understanding of it is limited by our own knowledge and imagination. The ancient world was not a simple place populated by simple people. It was a world of great sophistication, great ingenuity, and great diversity, a world in which millions of human minds worked on the problems of their time with the same intelligence and creativity that we bring to the problems of ours. The Baghdad Batteries are a reminder that those minds sometimes found solutions that we did not expect, and that the history of human technology may be far more complicated and far more interesting than the neat, linear narrative we have constructed to explain it. Let us now turn to the question of what the ancient peoples of Mesopotamia actually knew about the materials and phenomena that are relevant to the Baghdad Batteries, because the batteries did not appear in a vacuum. They were the product of a culture with deep and extensive knowledge of metallurgy, chemistry, and the natural world. The metallurgical traditions of Mesopotamia are among the oldest and most sophisticated in the world. Copper was being smelted in the region as early as the 5th millennium before the Common Era, more than 7,000 years ago. Bronze, an alloy of copper and tin, was in widespread use by the 3rd millennium before the Common Era, and its production required a detailed understanding of ore processing, furnace design, alloying ratios, and casting techniques. Iron smelting followed in the 2nd millennium before the Common Era, and by the time of the Parthian period, Mesopotamian metallurgists were working with a wide range of metals and alloys, including gold, silver, copper, iron, lead, tin, and mercury. The production of these metals required knowledge of chemistry, even if the ancient metallurgists did not call it by that name. They understood that certain rocks, when heated to high temperatures in the presence of charcoal, would yield metal. They understood that different metals had different properties, that some were harder, some softer, some more resistant to corrosion, some more ductile. They understood that metals could be combined to produce alloys with properties different from those of the constituent metals. And they understood that metals interacted with other substances in predictable ways, that iron rusted when exposed to water, that copper turned green when exposed to air, that gold resisted corrosion almost completely. This body of knowledge, accumulated over millennia of trial and error, provided the foundation upon which the Baghdad Batteries could have been built. The ancient metallurgists of Mesopotamia knew copper and iron intimately. They knew how to work these metals, how to shape them, how to solder them. They knew the properties of bitumen and how to use it as a sealant. They had access to acidic substances, vinegar, wine, citric acid from fruits, and mineral acids that seep from the ground in certain parts of the region. All the materials needed to build a Baghdad battery were readily available to a Mesopotamian craftsman with even a modest level of skill and knowledge. But knowledge of materials is not the same as knowledge of principles. Did the ancient Mesopotamians understand electricity? Did they know what they were creating when they assembled these jars? Or were the batteries a product of empirical observation, a device that was discovered to work without any understanding of why it worked? This is a question that we cannot answer with certainty, but we can make some informed observations. In the history of technology, it is extremely common for practical knowledge to precede theoretical understanding. People used fire for hundreds of thousands of years before they understood combustion. Farmers bred plants and animals for thousands of years before anyone understood genetics. Navigators used the stars for millennia before anyone understood celestial mechanics. The gap between knowing how and knowing why is one of the great themes of human intellectual history, and it applies as much to the Baghdad Batteries as it does to any other technology. It is entirely plausible that an ancient craftsman, working with copper and iron in an acidic solution, noticed that the metals reacted in an unusual way, that a tingling sensation could be felt when both metals were touched simultaneously, that a faint spark could be seen in certain conditions, or that a thin layer of one metal could be deposited on another when the two were immersed together in the right kind of liquid. This craftsman would not have understood electrons or ions or oxidation-reduction reactions, but he would have understood that something was happening, something useful, something reproducible, and he would have refined his technique, built standardized devices to exploit the effect, and passed his knowledge on to his apprentices. This is how technology usually develops. Not through sudden flashes of theoretical insight, but through the slow, patient accumulation of practical knowledge, one observation at a time, one experiment at a time, one generation at a time. The Baghdad Batteries may be the product of exactly this kind of process, a technology that was developed empirically, used practically, and never accompanied by a theoretical understanding of the principles that made it work. There's another dimension to the Baghdad Battery story that is often overlooked, and that is the question of precedent. Were the Baghdad Batteries the first electrochemical devices in human history, or were they the culmination of an even older tradition? This question is difficult to answer because the evidence is sparse. Very few ancient artifacts have been examined with the possibility of electrochemical function in mind, and those that have been examined have not always yielded clear results. But there are intriguing hints that the knowledge behind the Baghdad Batteries may have roots that extend back even further than the Parthian period. Consider the ancient Egyptians. Egyptian goldsmiths produced some of the most exquisite metalwork in the ancient world, and some of their techniques have puzzled modern researchers. Gold-plated objects from Egyptian tombs sometimes display a quality of gilding that is difficult to explain by conventional methods alone. The gold layer is extremely thin, extremely uniform, and adheres to the base metal with a strength that suggests more than simple mechanical bonding. Some researchers have speculated that the Egyptians may have used a form of electroplating, although no direct evidence of batteries or electrochemical devices has been found in any Egyptian context. Consider also the ancient Indians. The Vedic texts, some of the oldest literary works in the world, contain references to a substance called Agastya Samhita, which some interpreters have claimed describes a device remarkably similar to an electrochemical cell. According to these interpretations, the text describes a vessel containing copper, zinc, and an acidic solution, which was used to produce a mysterious force or energy. The reliability of these interpretations is hotly debated, and many scholars dismiss them as misreadings or wishful thinking. But the possibility that electrochemical knowledge existed in ancient India, independent of or in connection with the Mesopotamian tradition, cannot be entirely ruled out. Consider the Chinese, who were among the most innovative metallurgists of the ancient world. Chinese craftsmen developed techniques for copper plating and gold plating that were in use as early as the Warring States period, roughly the 5th to 3rd centuries before the Common Era. Some of these techniques may have involved electrochemical processes, although the evidence is ambiguous. The Chinese also had extensive knowledge of acids, both organic and mineral, and of the reactions between metals and acidic solutions. If any ancient civilization had the knowledge base to develop electrochemistry independently, it was China. The point is not that electrochemistry was definitely known in ancient Egypt, India, or China. The evidence is too fragmentary to support such a strong claim. The point is that the Baghdad Batteries did not exist in isolation. They were part of a larger world of ancient metallurgy and chemistry that was far more sophisticated than we commonly assume, and that may have included knowledge and practices that have been lost and forgotten. Let us now address one of the most persistent and controversial aspects of the Baghdad Battery debate, the question of what happened to the original artifacts. The Baghdad Batteries were housed in the National Museum of Iraq in Baghdad, where they had been stored since their discovery in the early 1930s. The museum was one of the great repositories of Mesopotamian artifacts in the world, holding collections that span more than 7,000 years of human history, from the earliest Sumerian city-states to the Islamic Golden Age. The batteries occupied a modest corner of the museum's vast holdings, important to specialists but not well known to the general public. In 2003, during the invasion of Iraq, the National Museum of Iraq was looted. In the chaos that followed the fall of Baghdad, the museum was left unguarded, and looters entered the building and took thousands of artifacts. The looting was one of the greatest cultural catastrophes in modern history, comparable in scale and significance to the destruction of the Library of Alexandria or the sacking of Constantinople. Cuneiform tablets, cylinder seals, jewelry, sculptures, and countless other irreplaceable objects were stolen, damaged, or destroyed. The fate of the Baghdad Batteries during the looting is a matter of some uncertainty. Some sources report that the batteries were among the objects stolen from the museum. Others report that they were stored in a vault that was not breached by the looters. The exact status of the original artifacts remains unclear, in part because the chaos of the looting made a complete inventory impossible, and in part because the political instability that followed made it difficult for researchers to access the museum and its records. What is certain is that the looting of the National Museum of Iraq dealt a devastating blow to the study of the Baghdad Batteries. Even before the looting, the batteries had been difficult to study. Iraq's political isolation during the late 20th century had limited access to the museum's collections, and relatively few researchers had been able to examine the original artifacts firsthand. Most of the scientific analysis of the batteries had been conducted on replicas rather than originals. After the looting, the situation became even worse. The original artifacts, if they survived, were inaccessible, and the documentation and records associated with them were incomplete or missing. This is a tragedy not only for the study of the Baghdad Batteries, but for the study of ancient Mesopotamian civilization as a whole. The artifacts that were lost or damaged during the looting of the museum represent an irreplaceable record of human achievement, a record that took thousands of years to create and that was destroyed in a matter of days. The Baghdad Batteries, whatever they were part of that record. Their loss, if indeed they were lost, is a loss for all of humanity. Despite the uncertainties surrounding the original artifacts, the Baghdad Battery debate continues, and in recent years it has been enriched by new perspectives and new methods of analysis. One area of active research is the chemical analysis of the corrosion products found on the copper cylinders and iron rods of the original batteries. Corrosion products, the residues left behind when metals react with their environment, can provide valuable information about the conditions to which the metals were exposed. By analyzing the chemical composition and structure of these corrosion products, researchers can determine what kind of solution was in contact with the metals, how long the metals were immersed, and what kind of electrochemical reactions, if any, took place. Early analyses of the Baghdad battery metals suggested that the corrosion patterns were consistent with exposure to an acidic solution, supporting the hypothesis that the jars were used as electrochemical cells. More recent analyses, using advanced techniques such as X-ray diffraction, scanning electron microscopy, and energy dispersive spectroscopy, have provided more detailed information about the corrosion products, but the results have been mixed. Some studies support the electrochemical hypothesis. Others suggest that the corrosion could have been caused by natural processes over 2,000 years of burial without any need to invoke electrochemistry. The difficulty lies in distinguishing between corrosion caused by intentional use and corrosion caused by accidental exposure. If the jars were buried in soil that contained naturally occurring acids, which is common in the geology of the Baghdad region, the metals could have corroded in ways that mimic the effects of electrochemical activity. This makes it difficult to use corrosion analysis alone as definitive proof that the batteries were used as electrical devices. Another area of research is the study of ancient metallurgical techniques, particularly the methods used for gilding and plating metal objects. As analytical techniques have improved, researchers have been able to examine ancient gilded objects with unprecedented precision, measuring the thickness, uniformity, and chemical composition of gold layers at the nanoscale. Some of these analyses have revealed gilding techniques that are consistent with electroplating. Others have shown that the gilding was achieved by conventional methods such as mercury gilding or diffusion bonding, which do not require electricity. The picture that emerges from this research is complex. It is clear that the ancient metallurgists of Mesopotamia had access to a variety of gilding techniques, some of which may have involved electrochemistry, and some of which definitely did not. The Baghdad batteries may have been one tool among many in the metalworker's arsenal, used for specific applications where their unique capabilities offered an advantage over conventional methods. Or they may have been used for an entirely different purpose, one that had nothing to do with metalworking at all. The truth is that we do not know, we may never know. The evidence is too fragmentary, the artifacts too few, and the cultural context too distant for us to reach a definitive conclusion. But the uncertainty itself is valuable because it reminds us that the past is not a closed book. It is an open question, a puzzle that grows more interesting the more we learn about it, a challenge to our assumptions about what was possible and what was known in the ancient world. Let us return one final time in this first part of our exploration to the fundamental question that the Baghdad Batteries pose. Not what were they used for, but what do they mean? They mean that the story of human technology is not a straight line. It is a tangled web of discoveries and losses, of knowledge gained and knowledge forgotten, of innovations that flourished in one place and time and then vanished without a trace. They mean that our ancestors were more capable, more curious, and more creative than we often give them credit for. They mean that the history of science and engineering is not a modern monopoly, that people in every age and every culture have observed the world around them, asked questions about how it works, and devised ingenious solutions to the problems they faced. The Baghdad Batteries may have been simple devices, capable of producing only a small amount of electricity for a limited number of purposes. Or they may have been the visible tip of a much larger body of knowledge, a body of knowledge that included an understanding of electrical phenomena far beyond what the surviving evidence can demonstrate. We cannot know because we have only the jars themselves, and the jars do not speak. They sit in silence, their copper and iron corroded by time, their asphalt seals cracked and crumbling, their secrets locked away behind 2,000 years of history, but they ask us to wonder. They ask us to consider the possibility that the world our ancestors inhabited was richer and more complex than we have imagined. They ask us to look at the past not with condescension but with respect, not with certainty but with curiosity, not with the assumption that everything important has already been discovered, but with the humility to admit that there is much we do not know. The Baghdad Batteries are small objects. They fit in the palm of a hand, but the questions they raise are enormous. They reach across the centuries, from the dusty workshops of ancient Parthia to the gleaming laboratories of the modern world, and they connect us in a strange and intimate way to the nameless craftsmen who built them. Those craftsmen, whoever they were, understood something about the natural world that their contemporaries did not. They captured a force that would not be formally identified for nearly 2,000 years. They held lightning in a jar, and then they were forgotten. The jars were buried. The knowledge was lost. The world moved on unknowing for 2 millennia until construction workers in the outskirts of Baghdad broke through the earth and brought the past back into the light. That is the story so far, but it is not the complete story. There are more questions to ask, more evidence to examine, more theories to consider. There are connections to be drawn between the Baghdad Batteries and other anomalous artifacts from the ancient world. There are experiments to describe, debates to explore, and mysteries to unravel. The story of the Baghdad Batteries is not a story with a neat ending. It is a story that is still being written, still being debated, still challenging our understanding of what was possible in the ancient world. In the second part of this exploration, we will delve deeper. We will examine the broader context of ancient technology, the lost sciences of Mesopotamia, Egypt, India, and Greece. We will look at the work of modern researchers who have attempted to replicate and extend the capabilities of the Baghdad Batteries. We will explore the most controversial theories about ancient electricity, from the Dendera reliefs of Egypt to the legends of perpetual lamps in Roman temples. We will confront the question of whether ancient civilizations possessed knowledge that we have not yet rediscovered. And we will ask what the Baghdad Batteries tell us ultimately about the nature of human ingenuity and the fragility of human knowledge. The jars are waiting, the questions remain, and the past, as always, has more to reveal than we expect. Before we continue to the second part, let us pause and consider one more dimension of this mystery, one that is perhaps the most unsettling of all. The Baghdad Batteries were not unique. They were not a one-off invention, a single device created by a single eccentric genius and then discarded. They were manufactured. Multiple specimens were found, all with the same basic design, all from the same period, all from the same region. This implies standardization. This implies production. This implies that someone somewhere was making these devices in quantity, that there was a demand for them, that they served a purpose that was recognized and valued by the community that produced them. Think about what that means. If a single battery had been found, it could be dismissed as an anomaly, a freak of nature, an accidental assemblage of materials that happened to resemble a modern device. But multiple batteries, all built to the same specifications, all found at the same site, all dating to the same period, cannot be dismissed so easily. They represent a technology, a practice, a tradition. They represent knowledge that was shared, taught, and replicated. They represent a community of practitioners who understood how to build these devices and had a reason to do so. Who were these practitioners? We do not know their names. We do not know whether they were craftsmen, priests, physicians, or something else entirely. We do not know how they discovered the electrochemical effect that the batteries exploit. We do not know how they transmitted their knowledge, whether through written texts that have been lost, oral traditions that have been forgotten, or apprenticeship systems that died with the last practitioner. We do not know how long the tradition lasted, whether it persisted for generations or was the brief flowering of a single workshop that produced a few dozen devices before falling silent. What we do know is that they existed, that they had knowledge we did not expect them to have, that they built devices we did not think they could build, and that their knowledge, whatever it was lost so completely that the modern world had to rediscover it from scratch, oblivious to the fact that someone had walked this path before. This is the haunting reality of the Baghdad Batteries. Not that they prove ancient civilizations had electricity, because they do not prove that, not conclusively, but that they reveal how much we have lost. How much knowledge has been swallowed by the earth, buried under the rubble of fallen empires, dissolved in the acids of time. The Baghdad Batteries are a crack in the surface of history, a glimpse into a depth that we cannot fully fathom, a reminder that the past is not behind us, it is beneath us, and it is full of surprises. We are often told that history is written by the victors, but that is only half the truth. History is also erased by the conquerors, forgotten by the survivors, and misunderstood by those who come after. The Baghdad Batteries are a testament to this erasure, this forgetting, this misunderstanding. They survived by accident, preserved by the indifferent chemistry of clay and earth and time. They could just as easily have been destroyed, ground to dust by the weight of the centuries, their copper and iron and bitumen scattered beyond recognition. That they survived at all is a minor miracle. That someone recognized them for what they might be is another, and so we are left with questions, questions that cannot be answered by the artifacts alone. Questions that require us to look beyond the jars, beyond the site at Kujat Rabu, beyond the borders of ancient Parthia, and into the wider world of ancient knowledge and ancient technology, because the Baghdad Batteries did not exist in a vacuum. They were part of a world that was connected by trade routes and cultural exchanges that spanned continents, a world in which ideas and techniques flowed from east to west and from west to east, a world in which the boundaries between science and religion, between craft and art, between the practical and the mystical, were far more fluid than they are today. In that world, the Baghdad Batteries make sense. They are not anomalies. They are not impossibilities. They are the natural product of a civilization that had been working with metals for thousands of years, that had access to a wide range of chemicals and materials, that had a tradition of empirical experimentation and practical problem solving that predates the formal scientific method by millennia. They are evidence not of alien intervention or lost super-civilizations, but of the ordinary, extraordinary genius of the human mind, working with the materials at hand to solve the problems of the moment. And that, perhaps, is the most important lesson of the Baghdad Batteries. Not that ancient people had electricity, although they may have. Not that we have underestimated the technological capabilities of the past, although we certainly have. But that human ingenuity is a constant. It does not belong to any one era, any one culture, any one civilization. It is the birthright of every human being who has ever looked at the world and asked, how does this work and what can I do with it? The Parthian craftsman who built the first Baghdad battery was asking the same question that Volta asked, that Faraday asked, that Edison asked, and he found an answer. A small answer, perhaps, a limited answer, but an answer nonetheless. The Baghdad batteries are his legacy, and ours. That is where we will pause for now, but the story is far from over. In the second part of this documentary, we will go deeper into the mystery. We will explore the alternative theories in greater detail. We will examine the connections between the Baghdad batteries and other enigmatic artifacts from the ancient world. We will follow the trail of evidence across continents and centuries, from the temples of ancient Egypt to the workshops of classical Greece, from the laboratories of medieval alchemists to the lecture halls of modern universities. We will hear from the researchers who have devoted their careers to understanding these objects and from the skeptics who challenge their conclusions. the Baghdad Batteries are more than a curiosity. They are a challenge to our assumptions, our certainties, and our understanding of the past. They remind us that history is not a finished product. It is a process, a conversation between the present and the past, a dialogue that is never truly complete. The jars are still speaking, we just have to learn how to listen. As we bring this first part to its close, let us take a moment to appreciate the sheer improbability of the Baghdad Battery story. Here is an artifact that was pulled from the earth by construction workers who had no idea what they had found. It sat in a museum for years before anyone recognized its significance. It was identified as a possible battery by a painter turned archaeologist who happened to have the right combination of knowledge and curiosity. It was tested by an electrical engineer who was intrigued enough to build a replica. It was used to electroplate a figurine by a museum researcher who wanted to prove a point. And through all of this, through all the accidents and coincidences and strokes of luck that brought the Baghdad Batteries to our attention, the question of their true purpose remains unanswered. This is archaeology at its most fascinating and its most frustrating. The evidence points in multiple directions. The theories are plausible but unproven. The original artifacts may be lost, damaged, or inaccessible. And the people who made the batteries, the only people who could tell us what they were for, have been dead for 2,000 years. But the questions remain. And questions in the end are more valuable than answers because they drive us to keep searching, keep thinking, keep digging, both literally and metaphorically, into the earth and into the past. The Baghdad Batteries are an invitation to wonder, and wonder is the beginning of all knowledge. We will continue this journey in the second part. Until then, consider this. 2,000 years ago, in a small workshop in the ancient land between the rivers, someone held a clay jar in their hands. They fitted it with a copper tube and an iron rod. They sealed it with bitumen. They filled it with vinegar or wine or some other acidic liquid, and when they touched the two metals they felt something, a tingle, a spark, a force that had no name, no explanation, no precedent in their experience of the world. What did they think? What did they do? What did they understand? We do not know, but we know this. They built more of them. They refined the design. They used them for something important enough to justify the labor of assembling copper and iron and bitumen, something important enough to produce not one but a dozen of these devices, something important enough to make them a part of their daily lives. And then one day they stopped. The workshop fell silent. The craftsman laid down his tools. The last battery was sealed with its plug of bitumen and placed on a shelf, or buried in the earth, or left on a workbench to be covered by the slow accumulation of dust and debris in centuries. And the world forgot. Until one day a shovel struck clay and the past broke through the surface of the present and the Baghdad Batteries began to speak again. The question is whether we are ready to hear what they have to say. The ancient world was a place of wonders, both recognized and unrecognized. The great library of Alexandria held the accumulated knowledge of the Greek-speaking world, and much of that knowledge was lost when the library was destroyed. The engineers of Rome built aqueducts that carried water across valleys and over mountains, using principles of fluid dynamics that would not be formally articulated for more than 1,000 years. The astronomers of Babylon tracked the movements of the planets with a precision that astonishes modern scientists. The metallurgists of India produced iron pillars that have resisted corrosion for 16 centuries, using techniques that modern materials science is only beginning to understand. In this context, the Baghdad Batteries are not an anomaly. They are a piece of a larger puzzle, one that includes dozens of unexplained artifacts and inexplicable achievements from civilizations across the ancient world. They are part of a pattern of lost knowledge, of forgotten discoveries, of technologies that were born and died with the civilizations that created them. This pattern raises profound questions about the nature of progress and the permanence of knowledge. We tend to assume that once something is discovered, it stays discovered. That knowledge, once gained, is never truly lost, but the evidence suggests otherwise. Knowledge can be lost, technologies can be forgotten. Entire sciences can vanish from human awareness as completely as if they had never existed. The Baghdad Batteries are a sobering reminder of this truth. They tell us that we are not the first to discover electricity. They tell us that we are not the first to harness the power of chemical reactions. They tell us that we are not the first to wonder about the invisible forces that animate the natural world. We are the latest in a long line of questioners, a line that stretches back not merely centuries but millennia, a line that includes the nameless craftsmen of ancient Parthia who held lightning in a clay jar and for a brief shining moment understood something about the world that would not be understood again for 2,000 years. Their knowledge was lost. Ours might be too. That is the ultimate lesson of the Baghdad Batteries. Not that the past was more advanced than we think, although it may have been. Not that we have underestimated our ancestors, although we certainly have. But that knowledge is fragile, that progress is not inevitable, that the achievements of one generation can be wiped out by the failures of the next, and that the only way to prevent that loss is to value what we know, to protect it, to share it, and to never, ever take it for granted. The Baghdad Batteries were forgotten for 2,000 years. What will be forgotten next? That question, heavy as it is where we leave you for now. But take heart, the story continues, the mystery deepens. And in the second part of this documentary, we will pursue the truth wherever it leads, into ancient temples and modern laboratories, across deserts and through centuries, following the faint trail of evidence that the Baghdad Batteries have left behind. The past is not dead. It is not even past. It is alive, buried beneath our feet, waiting to be discovered. And sometimes, when the earth opens and the light falls on something that has been hidden for millennia, the past speaks to us in a language we can almost understand. The Baghdad Batteries are speaking. Listen carefully. The story is just beginning. Welcome back. In the first part of this documentary, we examine the discovery and physical characteristics of the Baghdad Batteries, the Parthian-era clay jars found near Baghdad that appear to function as electrochemical cells. We explored the theories of electroplating, medical therapy, and religious spectacle. We considered the skeptics' objections and the broader context of Mesopotamian civilization. And we confronted the unsettling possibility that a working knowledge of electricity existed in the ancient world 2,000 years before Volta, Faraday, and the dawn of the electrical age. Now we go deeper, because the Baghdad Batteries do not exist in isolation. They are not the only anomalous artifacts from the ancient world that hint at technological knowledge far beyond what mainstream history acknowledges. Across the ancient world, from the temples of Egypt to the workshops of Greece, from the forges of India to the laboratories of medieval alchemists, there are traces, fragments, whispers of knowledge that does not fit neatly into our conventional timeline of discovery. Some of these traces are well documented, others are speculative. All of them are fascinating, and when viewed together alongside the Baghdad Batteries, they suggest a picture of the ancient world that is far more complex, far more capable, and far more mysterious than the one we have been taught. This is the story of that wider mystery, and it begins, as so many stories about the ancient world do, in Egypt. In the Temple of Hathor at Dendera, a site on the western bank of the Nile in Upper Egypt, there is a series of stone reliefs carved into the walls of a subterranean crypt. The temple itself dates to the Ptolemaic period, roughly the 1st century before the Common Era, though it was built on the foundations of much older structures, and the traditions it embodies may stretch back thousands of years further. Hathor was the goddess of love, beauty, music, and joy, one of the most beloved deities in the Egyptian pantheon, and her temple at Dendera was one of the great pilgrimage sites of the ancient world. The reliefs in question are located in a narrow chamber beneath the main temple, a space that was not accessible to ordinary worshippers and that appears to have been reserved for the highest-ranking priests. The carvings depict a series of figures engaged in what appears to be a ritual or ceremonial activity. The central element of the scene is a large, bulbous object, elongated and tapering at one end, resting on a pillar or stand. Inside the bulbous object is a wavy line, a serpentine form that extends from one end to the other. At the narrow end of the object, a cable or cord appears to connect it to a box-like structure on the ground. A figure, possibly a priest or deity, stands beside the object, sometimes touching it, sometimes holding it aloft. To the untrained eye, these reliefs are obscure. They could be depictions of a lotus flower, which was a common symbol in Egyptian art. They could be representations of a mythological scene, perhaps the birth of a divine serpent or the emergence of a god from the primordial waters. Egyptian art is rich in symbolism, and many of its images are open to multiple interpretations. But to some observers, the Dendera reliefs look like something else entirely. They look like light bulbs. The bulbous object, according to this interpretation, is a glass envelope, similar to the evacuated glass tube of a modern incandescent or gas discharge lamp. The serpentine line inside it is a filament or an electrical discharge, the glowing element that produces light. The cable connecting the object to the box on the ground is a power cord, and the box itself is a power source, perhaps a battery or a generator. The pillar on which the object rests is an insulating stand, designed to prevent the electrical current from grounding out. This interpretation, known as the Dendera light hypothesis, was popularized in the 1970s and 80s by a number of writers and researchers, most notably the Austrian authors Peter Krasse and Reinhard Habeck, who published a book on the subject that attracted widespread attention. According to their theory, the ancient Egyptians possessed a form of electrical lighting technology, powered by devices similar to the Baghdad Batteries, that they used to illuminate the dark interior chambers of their temples and tombs. The Dendera light hypothesis is one of the most controversial claims in the entire field of alternative archaeology. Mainstream Egyptologists reject it overwhelmingly, arguing that the reliefs are consistent with conventional Egyptian artistic and mythological traditions, and that the resemblance to a light bulb is superficial and coincidental. The serpentine form, they argue, is clearly a snake, a common motif in Egyptian religious art that represents the god Harsamtis emerging from a lotus flower. The pillar is a jed pillar, a well-known Egyptian symbol associated with the god Osiris and representing stability and endurance. The cable is a lotus stem. The box is a standard depiction of a shrine or sanctuary. These objections are serious and well-founded. Egyptian art follows strict conventions, and the elements of the Dendera reliefs can all be explained within the framework of those conventions without invoking electricity. The resemblance to a light bulb may be nothing more than pareidolia, the human tendency to see familiar patterns in random or ambiguous stimuli. We see faces in clouds, animals in rock formations, and light bulbs in ancient carvings, not because the patterns are there, but because our brains are wired to find them. And yet the Dendera light hypothesis persists, not because it has been proven, but because it raises questions that have not been fully answered. The most compelling of these questions is practical. How did the ancient Egyptians illuminate the interior chambers of their temples and tombs? Many of these chambers are located deep underground, far from any source of natural light. The walls of these chambers are covered with intricate, detailed paintings and carvings that required sustained, bright illumination to produce. Yet no soot deposits have been found on the ceilings or walls of many of these chambers, soot that would inevitably accumulate if the chambers were illuminated by torches, oil lamps, or candles over the long periods required to complete the artwork. This is a genuine puzzle. Ancient torches and oil lamps produce significant amounts of soot, a black, greasy residue that settles on surfaces near the flame. In chambers with poor ventilation, such as the underground crypts and burial chambers of Egyptian temples and tombs, soot accumulation would be rapid and substantial. Yet in many of these chambers, the ceilings and upper walls are remarkably clean. The paint is vivid and unblemished. There is no visible soot layer. Several explanations have been proposed for this absence of soot. One is the use of polished metal mirrors to reflect sunlight from the entrance of the temple deep into its interior, bouncing the light around corners and down corridors until it reached the innermost chambers. This technique is theoretically possible and has been demonstrated experimentally, but it has significant limitations. The intensity of the reflected light diminishes rapidly with each reflection, and the mirrors would need to be positioned and maintained with extreme precision to direct light to specific locations deep within a complex structure. In practice, the amount of light that could reach the innermost chambers by this method would be very small, probably insufficient for the detailed artistic work that was performed there. Another explanation is the use of low soot fuels, such as purified oils or waxes, in lamps designed to minimize smoke production. This is plausible, and some experimental evidence supports it. Lamps burning high-quality olive oil or castor oil produce less soot than those burning animal fat or crude plant oils. Specialized lamp designs with properly trimmed wicks and adequate ventilation can further reduce soot production. It is possible that the ancient Egyptians developed lamp technology specifically designed for use in enclosed spaces, producing enough light to work by without excessive soot accumulation. This is probably the correct explanation, or at least a large part of it, but it is not entirely satisfying because even the cleanest oil lamp produces some soot over time, and the sheer volume of artistic work in some Egyptian tombs implies hundreds or thousands of hours of sustained illumination. The absence of soot in these contexts remains a minor mystery, one that the Dendera light hypothesis, however improbable, attempts to address. The connection to the Baghdad Batteries is clear, at least in theory. If the ancient world possessed battery technology, and if that technology could be scaled up by connecting multiple cells in series, then it is conceivable, though by no means proven, that the resulting electrical power could have been used to create some form of lighting. A gas discharge tube, similar to a modern fluorescent lamp or neon sign, requires relatively low voltage to operate once the gas inside the tube is ionized. A bank of Baghdad batteries connected in series could potentially produce enough voltage to ionize a gas and create a sustained glow. This is, of course, highly speculative. There is no direct evidence that the ancient Egyptians had batteries, gas discharge tubes, or any form of electrical lighting. The Dendera reliefs, interpreted as light bulbs, are a visual similarity, not a proof, and the absence of soot in Egyptian tombs can be explained, however imperfectly, by conventional means. But the Dendera light hypothesis, like the Baghdad batteries themselves, serves as a reminder that the ancient world may have contained technologies and knowledge that we have not yet recognized. It is a provocation, an invitation to look more closely, to question our assumptions, and to remain open to the possibility that there is more to the story than we think. The idea that the ancient world possessed some form of electrical knowledge is not limited to the Baghdad batteries and the Dendera reliefs. There are other artifacts, other texts, other traditions that have been cited as evidence of ancient electrical phenomena, and while none of them are conclusive on their own, taken together they form a body of circumstantial evidence that is difficult to dismiss entirely. One of the most intriguing of these traditions involves the so-called perpetual lamps, lights that were said to burn without fuel in the tombs and temples of the ancient world, sometimes for centuries. Reports of perpetual lamps appear in the writings of numerous ancient and medieval authors, spanning a period of more than 1,000 years and covering a geographic range from Egypt to Rome to the Holy Land. The Roman writer Plutarch, who lived in the 1st and 2nd centuries of the Common Era, described a lamp in the Temple of Ammon in Egypt that was said to burn continuously without being refueled. Saint Augustine, the great Christian theologian of the 4th and 5th centuries, wrote about a lamp in a temple of Venus that could not be extinguished by wind or rain. The Byzantine scholar Cedrenus recorded the discovery of a perpetual lamp in a sealed tomb near Constantinople, which had been burning, according to the inscription on the tomb, for more than 500 years. The physician and alchemist Paracelsus, writing in the 16th century, described perpetual lamps as real and attributed them to the secret knowledge of the ancients. These reports are, of course, unreliable in the strict evidentiary sense. They are second-hand accounts, often written long after the events they describe, and they are colored by the credulity and the literary conventions of their times. Ancient and medieval writers were not above embellishment, exaggeration, or outright invention, and the concept of a lamp that burns forever has an obvious appeal as a symbol of divine power, eternal life, and the triumph of light over darkness. Many of the perpetual lamp stories are almost certainly legends, myths, or misinterpretations of natural phenomena, but the persistence and prevalence of these stories is noteworthy. They appear in multiple cultures, across multiple centuries, in sources that are otherwise generally reliable. And some of the accounts include details that are oddly specific, details about the type of fuel used, the design of the lamp, the conditions under which it was found, and the appearance of its flame, details that suggest at least some basis in observation, even if the observations were misunderstood or exaggerated. What could a perpetual lamp have been? If we set aside the supernatural explanation, several possibilities present themselves. One is phosphorescence, the phenomenon in which certain materials absorb light and then re-emit it slowly over time, producing a faint glow that can persist for hours or days after the light source is removed. Phosphorescent minerals are found in many parts of the ancient world, and it is conceivable that a sealed tomb containing phosphorescent materials could appear to glow when first opened, leading observers to believe that a lamp was burning inside. Another possibility is bioluminescence, the production of light by living organisms. Certain fungi, bacteria, and insects produce light through chemical reactions in their cells, and bioluminescent organisms are found in many environments, including underground caves and sealed spaces. A colony of bioluminescent fungi growing in a sealed tomb could produce a faint, eerie glow that might be mistaken for a perpetual flame. A third possibility, and the one most relevant to our discussion, is that some form of electrical or electrochemical technology was responsible. If the ancient world possessed battery technology, as the Baghdad Batteries suggest, then it is conceivable that a battery-powered light source could have been constructed. A sealed vessel containing an electrolyte and two metal electrodes could produce a sustained current for a significant period of time, and if that current were used to power a light-emitting device of some kind, the result might appear to be a lamp that burned without fuel. This is, again, highly speculative. There is no direct evidence linking the perpetual lamp tradition to electrochemical technology, but the existence of the Baghdad Batteries lends at least a degree of plausibility to the idea that the ancient world possessed some form of electrical capability, and the perpetual lamp tradition, however embellished and distorted by time, may preserve a distant echo of that capability. Let us now turn to another ancient tradition that has been linked, rightly or wrongly, to the question of ancient electricity. This is the tradition of the Ark of the Covenant, one of the most famous and mysterious objects in religious history. According to the Hebrew Bible, the Ark of the Covenant was a sacred chest built by the Israelites under the direction of Moses during their wandering in the Sinai desert after the Exodus from Egypt. The ark was made of acacia wood and overlaid with gold, both inside and out. It was fitted with two gold-covered poles for carrying and topped with a gold lid called the mercy seat, upon which two golden cherubim faced each other with outstretched wings. The ark was said to contain the stone tablets of the 10 Commandments, Aaron's rod, and a pot of manna. It was the most sacred object in Israelite religion, the dwelling place of the divine presence, and it was kept in the innermost chamber of the tabernacle and later the temple in Jerusalem. What makes the ark relevant to our discussion is a series of passages in the Hebrew Bible that describe dangerous encounters with the ark in the book of Samuel. For example, when the Philistines captured the ark and placed it in the temple of their god Dagon, the statue of Dagon was found fallen on its face the next morning. When the people of Beit Shemesh looked inside the ark, many of them were struck dead. When Uzzah, a man assisting in the transport of the ark, reached out to steady it when the oxen stumbled, he was struck dead on the spot. These accounts describe the ark as an object of immense and dangerous power, an object that could kill those who touched it or approached it without proper precautions. Some researchers have noted that the construction of the ark, as described in the book of Exodus, bears a striking resemblance to a large capacitor, a device for storing electrical charge. A capacitor consists of two conductive surfaces separated by an insulating material, or dielectric. When a charge is applied to one surface, it induces an opposite charge on the other surface, and the resulting electrical energy is stored in the dielectric between them. The ark, with its gold-covered wooden box, could be interpreted as a capacitor, with the gold layers serving as the conductive surfaces and the acacia wood serving as the dielectric. If the ark accumulated a static charge, either from the dry desert atmosphere or from some deliberate mechanism, it could have delivered a powerful electric shock to anyone who touched it without proper grounding. This interpretation was proposed by several researchers in the 20th century, and it has captured the popular imagination, but it must be treated with great caution. The Ark of the Covenant is a religious object described in a religious text, and the accounts of its powers are embedded in a narrative context that is theological rather than technological. The deaths attributed to the ark are presented in the Bible as divine punishments, not as electrical accidents, and interpreting them as evidence of ancient electrical technology requires reading the text in a way that is fundamentally at odds with its original purpose and meaning. Moreover, the capacitor interpretation has significant technical problems. A wooden box covered with gold, even if it could accumulate a static charge, would not store enough energy to kill a person. The capacitance of such a device would be extremely small, and the voltage, while potentially high, would be discharged in a single, brief spark rather than a sustained current. Static discharges can be painful and startling, but they are rarely lethal. The deaths described in the Bible would require a much larger energy source than a simple capacitor could provide. The Ark of the Covenant is a fascinating object, and the stories surrounding it are compelling. but the electrical interpretation of the arc is, at best, a creative speculation that tells us more about the interpretive frameworks of modern researchers than about the technological capabilities of the ancient Israelites. We mention it here not because it is proven or even probable, but because it illustrates the broader cultural fascination with the idea of ancient electricity and the lengths to which some researchers will go to find evidence of it in the historical record. Far more substantive than the arc hypothesis, and far more relevant to the Baghdad Batteries, is the question of ancient knowledge of static electricity. Because while the Baghdad Batteries represent a possible example of electrochemical electricity, the production of current from chemical reactions, there is abundant and unambiguous evidence that the ancient world was aware of static electricity, the production of electric charge through friction. The ancient Greeks knew that amber, when rubbed with fur or cloth, acquired the ability to attract small objects such as bits of straw, feathers, and hair. This phenomenon was first described by Thales of Miletus, one of the earliest Greek philosophers who lived in the 6th century before the Common Era. Thales observed that rubbed amber behaved as though it were alive, reaching out and grasping at nearby objects without any visible mechanism of action. He attributed this behavior to a soul or animating force within the amber, an interpretation that reflects the vitalistic worldview of early Greek philosophy. The Greek word for amber is electron, and it is from this word that we derive the modern terms electricity, electron, and electronics. The connection between ancient amber and modern electricity is not merely linguistic, it is conceptual. The ancient Greeks observed a phenomenon, the attraction of objects by rubbed amber, that is a direct manifestation of the electromagnetic force, one of the 4 fundamental forces of nature. They did not understand the mechanism behind it, but they recognized it, named it, and remembered it. And that recognition, passed down through centuries of philosophical tradition, eventually provided the foundation for the modern science of electricity. But the Greeks did more than just observe the amber effect. They also observed the related phenomenon of static discharge, the spark and crackle that occurs when a charged object is brought near a conductor. Anyone who has walked across a carpeted floor on a dry day and then touched a metal doorknob has experienced this phenomenon. In the ancient world, where woolen garments and dry climates were common, static discharges would have been a frequent and familiar occurrence. The ancients may not have understood the physics behind these sparks, but they certainly experienced them, and they may have recognized a connection between the sparks produced by rubbing amber and the much larger sparks produced by lightning. Indeed, several ancient writers drew explicit parallels between the amber effect and lightning. The Roman philosopher Lucretius, writing in the 1st century before the Common Era, discussed both phenomena in his great poem De Rerum Natura, on the nature of things, and suggested that they were manifestations of the same underlying force. This was a remarkably prescient insight, one that would not be confirmed until Benjamin Franklin's famous experiments with lightning in the 18th century. The ancient world then was not entirely ignorant of electrical phenomena. The Greeks knew about static electricity. The Romans knew about electric fish. The Egyptians depicted electric catfish in their tomb paintings. Physicians used torpedo rays as therapeutic devices, and the Parthians, or whoever built the Baghdad Batteries, may have discovered electrochemistry. Each of these pieces of knowledge is limited in itself, but together they suggest a broader awareness of electrical phenomena than is commonly acknowledged. The question is whether these separate observations were ever connected, whether anyone in the ancient world recognized that the amber effect, the torpedo ray, the lightning bolt, and the Baghdad Battery were all manifestations of the same fundamental force. The answer, almost certainly, is no. The unification of these phenomena into a single theory of electricity required concepts, the electron, the electromagnetic field, the conservation of charge, that were not available to ancient thinkers. The ancient world observed electrical phenomena, but it did not understand them. It experienced electricity, but it did not have a science of electricity. And yet the observations were made, the phenomena were noticed. The knowledge was there, scattered and fragmented, waiting for someone to put the pieces together. It would take nearly 2,000 years before that synthesis occurred. But the raw material, the empirical observations upon which the science of electricity was eventually built, existed in the ancient world long before the modern era. Let us now examine more closely the experiments that have been conducted on Baghdad Battery replicas in recent decades. because these experiments illuminate not only the capabilities of the ancient devices, but also the limits of our ability to draw conclusions from them. We have already discussed the pioneering experiments of Willard Gray in 1940 and Arne Eggebrecht in the 1970s, but these were not the only researchers to test the Baghdad Battery design. In the decades since König's original publication, dozens of experiments have been conducted by engineers, chemists, physicists, and enthusiasts around the world. The results have been consistent in some respects and variable in others, and they provide a detailed picture of what the Baghdad batteries could and could not do. The most basic finding, confirmed by every experiment, is that the Baghdad battery design produces voltage. A single cell filled with an acidic electrolyte consistently generates between approximately 0.4 and 1.9 volts, depending on the specific electrolyte used. Vinegar produces approximately 0.5 to 0.9 volts. Lemon juice produces slightly more. Grape juice, which is more acidic and contains a higher concentration of organic acids, produces up to about 1 volt. A solution of copper sulfate, a substance that was known and used in the ancient world, produces the highest voltage, up to about 1.5 to 1.9 volts per cell. The current produced by a single cell is much more variable and much more difficult to measure consistently. It depends on the surface area of the electrodes, the concentration and temperature of the electrolyte, the purity of the metals, and the resistance of the external circuit. In general, the current produced by a Baghdad battery replica is in the range of a few hundred microamperes to a few milliamperes. This is a very small current, far less than the current produced by a modern battery, but it is measurable and it is real. One important finding from the experimental work is that the Baghdad battery design is inherently unstable. The electrochemical reactions that produce the voltage also produce reaction byproducts, metal oxides, dissolved metal ions and gases that accumulate in the electrolyte and on the electrode surfaces over time, gradually reducing the efficiency of the cell. In addition, the iron rod, which serves as the anode, is gradually consumed by the oxidation reaction, becoming thinner and weaker until it eventually breaks or dissolves completely. A single Baghdad battery, filled with vinegar and left to operate continuously, will produce measurable voltage for a few days to a few weeks before the reaction slows to a trickle and the cell effectively dies. This limited lifespan is not unusual for a simple galvanic cell. Modern batteries also have finite lifespans, determined by the amount of reactive material available and the rate at which it is consumed. But it does have implications for the practical use of the Baghdad batteries. Whatever they were used for, it was probably not a continuous, long-term application. The batteries would have needed to be refreshed periodically, either by replacing the electrolyte, replacing the iron rod, or building an entirely new cell. This suggests that they were used intermittently for specific tasks or occasions, rather than as a continuous power source. Several experiments have specifically tested the electroplating hypothesis. Eggebrecht's original experiment, in which he successfully electroplated a silver figurine with gold using Baghdad battery replicas, has been replicated by other researchers with similar results. But the process is slow, much slower than modern electroplating. In Eggebrecht's experiment, the gold layer deposited on the figurine was extremely thin, only a few microns thick, and required several hours of continuous plating to achieve. Thicker layers would require proportionally longer plating times or higher currents, both of which are difficult to achieve with the Baghdad battery design. Some researchers have questioned whether the gold layer produced by Baghdad battery electroplating is truly comparable to the gold coatings observed on ancient Mesopotamian artifacts. Modern analysis of these ancient gold coatings has revealed a range of thicknesses and compositions, some of which are consistent with electroplating and some of which are not. Some ancient gold coatings show a diffusion gradient at the interface between the gold layer and the base metal, suggesting that the gold was applied by a thermal process such as mercury gilding or diffusion bonding rather than by electroplating. Others show a sharp, well-defined interface which is more consistent with electrodeposition. The evidence is mixed, and no single technique appears to account for all the observed gold coatings. Other experiments have tested the medical hypothesis. Researchers have applied the voltage from Baghdad battery replicas to various parts of the human body and measured the resulting sensations. At voltages of 0.5 to 1 volts, the sensation is barely perceptible, a faint tingle that can only be felt on the most sensitive areas of the skin, such as the fingertips or the tongue. At voltages of 2 to 5 volts achieved by connecting multiple cells in series, the sensation becomes more pronounced, a definite tingle or mild shock that is clearly noticeable but not painful. At voltages of 10 volts or more, the sensation becomes uncomfortable, and at higher voltages it can be genuinely painful. These results are consistent with the medical hypothesis. A bank of Baghdad batteries connected in series could produce a range of sensations, from a gentle tingle to a sharp shock, that could be applied to the body for therapeutic purposes. The experience of receiving an electric shock from an artificial device would have been deeply impressive to an ancient patient, and it is easy to imagine how such an experience could have been interpreted as evidence of healing power. One particularly interesting experiment was conducted by researchers who tested the effect of Baghdad battery replicas on acupuncture points, the specific locations on the body that are targeted in traditional Chinese and other Asian medical practices. The researchers found that the application of a small electrical current to certain acupuncture points produced measurable physiological effects, including changes in muscle tension, skin temperature, and blood flow. This finding is consistent with the principles of electroacupuncture, a modern therapeutic technique that uses electrical stimulation of acupuncture points to treat pain and other conditions. Whether the ancient Parthians practiced anything resembling acupuncture is unknown and seems unlikely, given the geographic and cultural distance between Mesopotamia and China. But the experiment does demonstrate that a small electrical current, of the magnitude produced by the Baghdad batteries, can have measurable effects on the human body, effects that could have been perceived and valued by an ancient practitioner even without any understanding of the underlying physiology. One of the most important developments in the Baghdad Battery story in recent decades has been the application of modern archaeological science to the question of the jar's original contents. What was the electrolyte? What liquid filled the jars and made them function as batteries? The answer to this question could shed significant light on the purpose of the batteries. If the electrolyte was vinegar, it would suggest a simple, readily available household substance, consistent with a technology that was widely accessible and possibly used for everyday purposes. If the electrolyte was wine, it would suggest a connection to religious or ceremonial practices, since wine had deep ritualistic significance in many ancient cultures. If the electrolyte was a solution of copper sulfate or another mineral substance, it would suggest a connection to metallurgy or craft production. Chemical analysis of residues found inside the original Baghdad battery jars has been limited, both by the small number of available specimens and by the difficulty of distinguishing between original contents and contaminants introduced during burial. Some analyses have detected traces of organic acids consistent with vinegar or wine. Others have detected traces of copper compounds consistent with a copper sulfate solution. Still others have found no identifiable residues at all, suggesting that the original contents had been completely decomposed or leached away over 2,000 years of burial. The most informative analysis was conducted on the bitumen seals of the jars. Bitumen, being a robust and durable material, preserves chemical information better than most organic substances. Analysis of the bitumen seals has revealed traces of organic compounds that are consistent with the presence of an acidic liquid, though the specific identity of the liquid cannot be determined with certainty. The results are suggestive but not definitive. More recently, researchers have attempted to use stable isotope analysis and other advanced chemical techniques to characterize the residues in the Baghdad battery jars. These techniques can provide information about the geographic origin, biological source, and chemical history of organic materials, and they have been used successfully to identify the contents of ancient vessels from other archaeological contexts. However, the application of these techniques to the Baghdad batteries has been hampered by the limited availability of samples and by the political and logistical difficulties of working with the collections of the National Museum of Iraq. The question of the electrolyte remains open, and it is a crucial question because the identity of the liquid that filled the jars is one of the few pieces of evidence that could directly indicate the purpose of the batteries. If we could determine what the ancient users put inside these jars, we would be a significant step closer to understanding what they used them for. Let us broaden our perspective now and consider the wider technological context in which the Baghdad batteries existed. Because the batteries were not the only remarkable technology of the ancient world, and understanding the broader landscape of ancient innovation can help us evaluate the plausibility and significance of the batteries themselves. The ancient world was far more technologically sophisticated than popular culture often suggests. We tend to imagine our ancient ancestors as primitive, living in mud huts and working with crude stone tools. But by the Parthian period, when the Baghdad batteries were made, human civilization had already produced achievements of breathtaking complexity and ingenuity. Consider metallurgy. By the time of the Parthians, metalworkers in the Near East had been refining their craft for more than 4,000 years. They could smelt copper, tin, lead, silver, and gold from ore. They could produce bronze and brass in precise alloy ratios. They could forge iron and steel, harden them by quenching, and temper them for resilience. They could cast metal objects in complex molds, using the lost wax technique to produce pieces of extraordinary detail and precision. They could gild objects with thin layers of gold or silver using mercury amalgamation, fire gilding, and other techniques. They could solder, braze, rivet, and weld. Their metallurgical knowledge was empirical, based on thousands of years of hands-on experience, but it was effective, and in some respects it rivaled the capabilities of modern metalworkers. Consider engineering. The Romans, contemporaries of the Parthians, built roads, aqueducts, bridges, harbors, and monumental buildings that still stand today. Their concrete, their arch construction, their water management systems, and their urban planning were achievements of stunning sophistication. The Parthians themselves were not far behind. They built cities, irrigation systems, and fortifications of considerable complexity. They maintained a network of trade routes, including sections of the Silk Road that required bridges, caravanserais, and other infrastructure. Their engineering was practical and effective, designed to solve real problems and serve real needs. Consider medicine. Ancient physicians, from the Egyptians to the Greeks to the Indians, had developed a detailed knowledge of human anatomy, pharmacology, and surgical technique. They performed cataract surgery, set broken bones, treated wounds with antiseptic substances, and compounded medicines from hundreds of plant, mineral, and animal ingredients. The surgical instruments found at Pompeii, preserved by the eruption of Vesuvius in 79 of the Common Era, include scalpels, forceps, retractors, catheters, and spicula that are recognizable, both in form and function, to modern surgeons. Ancient medicine was limited by a lack of germ theory and modern diagnostic tools, but within those limitations, it was remarkably effective. Consider astronomy. The Babylonians, whose intellectual traditions were inherited by the Parthians, had been observing and recording the movements of celestial bodies for more than 2,000 years by the time the Baghdad batteries were made. They could predict eclipses, calculate the length of the year to within minutes, track the movements of the planets with remarkable precision, and develop mathematical models of celestial motion that were not surpassed until the work of Kepler and Newton in the 17th century. Their astronomical knowledge was applied to the practical tasks of calendar making, agricultural planning, and navigation, and it was preserved in thousands of cuneiform tablets that have survived to the present day. In this context, the Baghdad batteries are not an inexplicable anomaly. They are a natural product of a culture that valued practical knowledge, empirical observation, and technological innovation. A civilization that could smelt metals, compound medicines, predict eclipses, and build aqueducts was certainly capable of discovering the electrochemical effect and building a device to exploit it. The question is not whether the ancient Parthians could have built batteries. The question is whether they did, and if so, what they used them for. There's a fascinating connection between the Baghdad batteries and the ancient tradition of alchemy, the proto-scientific practice that sought to understand and transform the nature of matter. Alchemy is often dismissed as a mere superstition, a misguided attempt to turn lead into gold through magical rituals and mystical incantations. But this dismissal is unfair and inaccurate. Alchemy was, in its origins, a serious empirical enterprise, a systematic effort to understand the properties of matter and to develop techniques for manipulating them. Many of the fundamental techniques of modern chemistry, distillation, sublimation, crystallization, calcination, and dissolution, were developed by alchemists. And the alchemical tradition, which flourished in the ancient and medieval worlds for more than 2,000 years, was deeply rooted in the metallurgical and chemical knowledge of ancient Mesopotamia. The earliest known alchemical texts date to the Hellenistic period, roughly the 3rd century before the Common Era to the 3rd century of the Common Era, the same period as the Baghdad Batteries. These texts were written in Greek and are attributed to various legendary figures, including Hermes Trismegistus, the mythical sage who was said to have possessed the ultimate secrets of nature. The Hellenistic alchemists drew heavily on Egyptian and Mesopotamian traditions, and their work represents a fusion of Greek philosophical concepts with the practical knowledge of Eastern craftsmen and metalworkers. Among the central concerns of ancient alchemy was the transformation of metals, the process by which base metals such as copper, lead, and iron could be converted into noble metals such as gold and silver. The alchemists believed that all metals were composed of the same fundamental substance, and that by manipulating the proportions and qualities of this substance, one metal could be transformed into another. This belief, while incorrect in its specifics, was not entirely unreasonable in the context of ancient metallurgy, where the smelting of ore into metal, the alloying of different metals to produce new substances, and the plating of one metal with another were everyday occurrences that seemed to demonstrate the mutability of matter. Electroplating, if it was practiced in the ancient world, would have been a powerful confirmation of the alchemical worldview. The ability to coat a base metal with gold, using nothing more than a clay jar filled with acidic liquid, would have seemed like genuine transmutation to an ancient observer. The base metal was literally being transformed into gold, not in its entirety, but on its surface, in a way that was visible, tangible, and undeniable. The process would have been regarded not merely as a useful craft technique, but as evidence of the fundamental truth of alchemical philosophy, proof that matter could be transformed, and that the secrets of nature could be unlocked through the application of the right knowledge and the right materials. This connection between the Baghdad Batteries and alchemy is speculative, but it is consistent with the cultural context of the Parthian period. Alchemy was a living tradition in the Hellenistic and Parthian worlds, practiced by scholars and craftsmen who were actively seeking to understand the nature of matter and to develop new techniques for working with it. The Baghdad Batteries, if they were used for electroplating, would have fit naturally into this tradition, providing both a practical technique and a philosophical inspiration. It is also worth noting that the alchemical tradition placed great emphasis on secrecy. Alchemical knowledge was considered sacred and dangerous, and it was transmitted through encrypted texts, symbolic language, and personal instruction from master to student. This culture of secrecy could explain why there are no explicit references to the Baghdad Batteries or to electroplating in ancient texts. The knowledge may have been deliberately concealed, hidden behind the veils of allegory and symbolism that characterize alchemical literature. If so, the Baghdad Batteries may be the physical evidence of a technology that was described in ancient texts in a form that we do not recognize, because we do not know how to read the coded language in which it was recorded. This is a tantalizing possibility, but it is also a dangerous one. The argument that absence of evidence is evidence of concealment is a logical trap that can be used to support virtually any claim. We must be careful not to project our desires onto the ancient record, seeing hidden messages where there are none and secret technologies where there are only ordinary objects. But we must also be careful not to dismiss the possibility of concealed knowledge out of hand, because the culture of secrecy in ancient alchemy is well documented, and the loss of alchemical knowledge through the destruction of texts and the death of practitioners is a historical fact. Let us now turn to a question that has been lurking in the background of our discussion from the beginning. If the Baghdad Batteries were genuine electrical devices, how did the knowledge behind them originate? Where did it come from? Was it the result of a long process of empirical discovery, or was it a sudden, accidental insight? We have already discussed the possibility that the batteries were the product of empirical observation, that an ancient craftsman noticed the electrochemical effect while working with copper and iron in an acidic solution, and then refined and standardized the technique. This is the most conservative and most plausible explanation, and it is consistent with what we know about how most ancient technologies were developed. But there is another possibility, one that is more dramatic and more difficult to evaluate. It is the possibility that the knowledge behind the Baghdad Batteries was not developed independently in Mesopotamia, but was transmitted from another culture through the vast networks of trade and cultural exchange that connected the ancient world. The Parthian Empire, as we have noted, was one of the most cosmopolitan states in the ancient world. It straddled the Silk Road, the great network of overland trade routes that connected the Mediterranean world to China, India, and Central Asia. Along these routes traveled not only goods, silk, spices, precious metals, and gemstones, but also ideas, technologies, religions, and philosophies. The Silk Road was one of the great engines of cultural diffusion in human history, and through it, knowledge flowed in both directions, from west to east and from east to west. We know that specific technologies were transmitted along the Silk Road. Papermaking, for example, was invented in China in the 2nd century before the Common Era and gradually spread westward, reaching the Islamic world by the 8th century of the Common Era and Europe by the 12th century. Gunpowder, another Chinese invention, traveled the same route in the opposite direction, eventually transforming warfare in Europe and the Middle East. Glass-making techniques developed in the Roman world spread eastward to India and China. Metalworking innovations moved in both directions, as did astronomical knowledge, mathematical concepts, and medical practices. Is it possible that the knowledge behind the Baghdad Batteries was transmitted along these routes? Could the electrochemical effect have been discovered in one culture and then carried to another by traveling merchants, itinerant craftsmen, or wandering scholars? This is a possibility that cannot be dismissed. The Silk Road was active during the entire period of the Baghdad Batteries manufacture, and the Parthian Empire, which controlled key sections of the route, was ideally positioned to receive and transmit knowledge from distant cultures. If electrochemical technology existed in China, India, or any other civilization along the Silk Road, it could have reached Mesopotamia through the normal channels of trade and cultural exchange. But there is no direct evidence for this scenario. No Baghdad Battery-like artifacts have been found in China, India, or any other culture along the Silk Road. No texts from these cultures describe electrochemical devices or processes that could be linked to the Baghdad Batteries. The hypothesis of Silk Road transmission remains a possibility, not a probability, and until supporting evidence is found, it must be treated as speculative. What is more certain is that the knowledge behind the Baghdad Batteries, wherever it originated, did not survive the fall of the civilizations that created it. The Parthian Empire fell to the Sassanid Persians in 224 of the Common Era, and the Sassanids, while they inherited many aspects of Parthian culture, do not appear to have preserved the battery technology. No Baghdad Battery-like artifacts have been found in Sassanid contexts. The knowledge was lost either because it was not transmitted to the new rulers, because it was deliberately suppressed, or because it was simply no longer considered useful or relevant. The loss of the battery technology is one of the most poignant aspects of the Baghdad Battery story. Here was a technology that worked, that could produce electricity, that had practical applications in metalworking, medicine, or religious practice, and yet it was forgotten. It did not survive the political and cultural upheaval of the Parthian-Sassanid transition. It did not spread to other cultures. It did not inspire further innovation or development. It simply vanished as if it had never existed, leaving behind nothing but a handful of clay jars buried in the earth. This is a reminder that technology, no matter how useful or innovative, is only as durable as the institutions that support it. Technology requires knowledge, and knowledge requires transmission. If the people who know how to build a device die without teaching others, the device dies with them. If the texts that describe a technique are destroyed, the technique is lost. If the economic or social conditions that make a technology useful change, the technology may be abandoned even if the knowledge to reproduce it still exists. The Baghdad Batteries were the product of a specific time, a specific place, and a specific set of cultural conditions. When those conditions changed, the batteries ceased to be made, and the knowledge behind them faded into oblivion. We must also consider the broader question of what the Baghdad Batteries tell us about the nature of scientific discovery itself. In the modern world, we tend to think of science as a cumulative enterprise, a steady march of progress in which each discovery builds on the last and leads inevitably to the next. We imagine a chain of knowledge stretching from the ancient Greeks to the medieval scholars to the Renaissance thinkers to the modern scientists, each link connected to the last in an unbroken sequence of intellectual advancement. But the Baghdad Batteries challenge this narrative. They suggest that scientific discovery is not always cumulative. It can be episodic, it can be local, it can be fragile. A discovery can be made, used, and then lost without leaving any trace in the larger intellectual tradition. The chain of knowledge can have gaps, missing links, broken connections, periods of darkness in which the light of understanding flickers and goes out, only to be rekindled centuries or millennia later by someone who has no idea that the light once burned before. This is a humbling thought. It means that our own scientific knowledge, however vast and powerful it may seem, is not immune to the same forces that destroyed the knowledge behind the Baghdad Batteries. War, political upheaval, cultural change, economic collapse, environmental disaster, any of these forces could disrupt the institutions that preserve and transmit our knowledge, and if they do, the knowledge could be lost, just as the battery technology was lost 2,000 years ago. We like to think that this could not happen in the modern world, that our knowledge is too widely distributed, too deeply embedded in our culture, too thoroughly documented to be lost, and perhaps that is true. The printing press, the internet, and the global network of universities and research institutions provide a degree of redundancy and resilience that ancient civilizations did not possess. But the history of the Baghdad Batteries is a cautionary tale. It tells us that no technology is permanent, no knowledge is secure, and no civilization is immune to the forces of decay and forgetting. Let us now examine some of the most recent scholarship on the Baghdad Batteries, because the debate has not ended. It has, if anything, intensified in recent years, as new analytical techniques and new theoretical perspectives have been brought to bear on the question. One of the most significant recent contributions to the debate has come from the field of experimental archaeology, which uses practical experiments to test hypotheses about ancient technologies. Several research groups have constructed large numbers of Baghdad Battery replicas and subjected them to systematic testing, varying the type of electrolyte, the size and shape of the electrodes, the temperature, and other variables. These experiments have confirmed the basic finding that the Baghdad Battery design produces voltage, but they have also revealed some unexpected results. One research group found that the voltage and current produced by a Baghdad Battery replica are significantly affected by the temperature of the electrolyte. At higher temperatures, the chemical reactions proceed faster, producing more current and maintaining a higher voltage for a longer period. At lower temperatures, the reactions slow down and the voltage drops. This finding suggests that the Baghdad Batteries would have been most effective in the hot climate of Mesopotamia, where ambient temperatures can easily exceed 40 degrees Celsius in the summer months. The warmth of the desert environment would have acted as a natural catalyst, enhancing the performance of the batteries and making them more useful for whatever purpose they served. Another research group tested the effect of different electrolytes on the longevity of the batteries. They found that a solution of copper sulfate not only produced the highest voltage but also lasted the longest, maintaining a measurable current for several weeks before the reaction slowed to a halt. Vinegar, by contrast, produced a lower voltage and a shorter operating life, with the current dropping to negligible levels within a few days. These results suggest that if the batteries were used for a purpose that required sustained current over a period of days or weeks, such as electroplating, a mineral electrolyte such as copper sulfate would have been the preferred choice. Yet another group of researchers focused on the question of connecting multiple batteries in series. They found that while connecting batteries in series does increase the total voltage, as expected, it also introduces problems of reliability. If any one cell in the series fails, either because its electrolyte is exhausted, its iron rod is consumed, or its seal develops a leak, the entire circuit is broken and no current flows. In a bank of 10 or 20 batteries, the probability of at least one cell failing at any given time is quite high, which means that the system would require constant monitoring and maintenance. This finding has implications for the practicality of the electroplating hypothesis, since a reliable electroplating operation would require a consistent and sustained power source, which a bank of Baghdad batteries could provide only with considerable effort and attention. These experimental findings do not resolve the debate about the Baghdad batteries, but they enrich it. They show that the ancient design is functional but limited, capable of producing electricity but not in the quantities or with the reliability that would be needed for many modern applications. They suggest that whatever the batteries were used for, it was a task that could tolerate intermittent and low-level current, a task that did not require the sustained, high-power output of a modern electrical system. There is one more line of evidence that deserves our attention, and it is perhaps the most provocative of all. In the years since König's original publication, several other artifacts from the ancient world have been identified as possible electrochemical devices, objects that bear a structural resemblance to the Baghdad Batteries and that may have served a similar purpose. One such artifact was reportedly discovered at a site in ancient Seleucia, a city on the Tigris River that was one of the great metropolises of the Hellenistic and Parthian worlds. The artifact, which dates to roughly the same period as the Baghdad Batteries, is described as a clay vessel containing copper and iron elements similar to those found in the Qujat Rabu jars. Unfortunately, the documentation of this find is incomplete, and the artifact itself may have been lost or destroyed during the turbulent history of the 20th century in Iraq. Its existence, if confirmed, would suggest that the Baghdad battery technology was not confined to a single site, but was more widely distributed across the Parthian world. Other possible electrochemical artifacts have been reported from sites in Egypt, though none of these reports has been confirmed to the satisfaction of mainstream archaeology. The difficulty is that many ancient artifacts that contain metal components could, in principle, function as electrochemical cells if filled with an acidic solution, even if they were not designed for that purpose. A copper vessel with an iron handle, for example, could produce a small voltage if filled with wine or vinegar, but that does not mean it was intended to be a battery. The challenge for researchers is to distinguish between artifacts that were designed to function as batteries and artifacts that merely happen to contain the right combination of materials by coincidence. This challenge is compounded by the fact that the archaeological record from the Parthian period is fragmentary and poorly documented. Many Parthian sites have been destroyed by modern development, looted by treasure hunters, or damaged by conflict. The archaeological heritage of Iraq, one of the richest in the world, has suffered enormously from the political instability and warfare that have plagued the region for decades. Many artifacts that might shed light on the Baghdad battery mystery have been lost, destroyed, or scattered into private collections where they are unavailable for study. The fragmentary nature of the evidence means that we may never have a complete picture of the Baghdad battery technology. We may never know how many batteries were made, how widely they were distributed, how long the technology was in use, or what purpose it served. We are left with a handful of artifacts, a collection of experiments, and a series of hypotheses, none of which can be definitively proven or disproven with the evidence currently available. And yet the Baghdad batteries continue to fascinate. They have been the subject of documentary films, popular books, academic papers, and countless online discussions. They have inspired engineers, historians, scientists, and dreamers. They have been claimed as evidence of ancient alien intervention, lost Atlantean technology, and secret knowledge preserved by hidden brotherhoods. They have been dismissed as ordinary pottery, misidentified ritual objects, and products of archaeological wishful thinking. They have been everything to everyone, a blank screen onto which we project our hopes, our fears, and our fantasies about the ancient world. But beneath all the speculation and sensationalism, there is a core of genuine mystery. The Baghdad batteries are real, they exist. They were made by human hands, assembled from common materials, designed to a consistent standard, and buried in the earth of ancient Mesopotamia. They can produce electricity. They are not magical or mystical. They are physical objects that obey the laws of nature, and they challenge us to explain how and why they were made. The honest answer is that we do not know. We do not know what the Baghdad batteries were used for. We do not know who made them. We do not know how the knowledge behind them was discovered. We do not know why it was lost. We have theories, some more plausible than others, but no certainties. The Baghdad batteries are one of those rare artifacts that sit at the intersection of the known and the unknown, the proven and the possible, the factual and the speculative. They are a reminder that the past is not a closed book but an open question, a question that may never be fully answered, but that is always worth asking. Let us now take a wider view still and consider what the Baghdad batteries mean for our understanding of the history of science. because the implications of these artifacts extend far beyond the specific question of ancient electricity. They touch on fundamental issues about the nature of knowledge, the process of discovery, and the relationship between technology and civilization. One of the most important lessons of the Baghdad Batteries is that scientific discovery is not the exclusive property of any single culture, era, or tradition. We tend to associate the history of science with a particular narrative, one that begins with the ancient Greeks, passes through the medieval Islamic world, and culminates in the scientific revolution of 17th century Europe. This narrative is not wrong, but it is incomplete. It privileges certain cultures and traditions at the expense of others, and it implicitly suggests that the capacity for scientific thought is a uniquely Western phenomenon. The Baghdad Batteries challenge this narrative. They suggest that the capacity for scientific and technological innovation is universal, that it exists in every human culture, in every era, in every corner of the world. The Parthian craftsman who built the first Baghdad Battery was not a Greek philosopher or a European scientist. He was a person of the ancient Near East, heir to a tradition of practical knowledge that stretched back thousands of years, working with the materials and the concepts available to him, and producing a device that was, by any measure, a genuine scientific achievement. This is not to say that the Baghdad Batteries represent a level of scientific understanding comparable to modern electrochemistry. They do not. The ancient craftsman who built them almost certainly did not understand the physics of electric current, the chemistry of oxidation-reduction reactions, or the mathematics of Ohm's law. He was working empirically by trial and error, guided by observation and experience rather than by theory. But his achievement was real nonetheless. He discovered something about the natural world that was true, useful, and reproducible. And he did it on his own without the benefit of modern education, modern instruments, or modern institutional support. This is the kind of achievement that deserves our respect and our attention, not because it proves that the ancient world was more advanced than we think, although it may have been. Not because it vindicates any particular theory about ancient technology, although some theories may be vindicated. But because it reminds us that human intelligence and creativity are not bounded by time or place. They are constants of the human condition, present in every generation, in every culture, in every individual who looks at the world and asks, how does this work? There is a philosophical dimension to the Baghdad Battery story that is worth exploring as well. The batteries raise the question of what we mean by technology and what counts as a genuine technological achievement. In the modern world, we tend to equate technology with complexity. We consider a technology to be advanced if it is complicated, if it requires specialized knowledge and sophisticated tools to produce, if it involves the manipulation of forces and materials that are invisible to the naked eye. By this standard, the Baghdad Batteries are not particularly impressive. They are simple devices made from common materials that produce a small amount of electricity. They are not computers, not nuclear reactors, not spacecraft. They are clay jars with copper tubes and iron rods, but this standard of evaluation is itself a product of our time and our culture. It reflects the values and priorities of a civilization that measures progress in terms of speed, power, and complexity. The ancient world had different values and different priorities. The ancient world valued durability, simplicity, and harmony with the natural environment. It valued the ability to create beautiful, functional objects from readily available materials, using techniques that could be learned and practiced by ordinary people. By this standard, the Baghdad Batteries are quite impressive. They are an elegant solution to a practical problem, a device that exploits a natural phenomenon using nothing more than clay, copper, iron, and vinegar. They require no rare materials, no specialized equipment, and no advanced theoretical knowledge. They are accessible, reproducible, and effective. This is a kind of technological genius that we tend to overlook in the modern world, the genius of simplicity. The ability to achieve a useful result with minimal resources and minimal complexity is a form of intelligence that is every bit as valuable as the ability to build a supercomputer or a particle accelerator, and it is a form of intelligence that the ancient world possessed in abundance. The Baghdad Batteries are an example of this genius. They are simple, but they are not crude. They are low-tech, but they are not primitive. They are a reminder that technology is not just about what you can build. It is about what you can build with what you have. As we approach the end of our exploration, let us return to the beginning. Let us return to the clay jars themselves, to the copper cylinders and the iron rods, to the asphalt seals and the acidic residues. Let us hold them in our minds as König held them in his hands more than 80 years ago, and let us ask, one final time, the question that has driven this entire investigation. What were they for? The honest answer, the only answer that the evidence currently supports, is that we do not know. We have theories, we have experiments, we have analogies and parallels and speculations, but we do not have proof. We do not have a text that says this is a battery and this is how it works and this is what we use it for. We do not have a workshop with batteries connected to electroplating baths. We do not have a medical text describing electrical therapy with clay jars. We do not have a temple with batteries hidden in the walls. What we have is a mystery, a genuine unsolved mystery of the ancient world. And that is, in a way, the most important thing about the Baghdad Batteries. Not that they answer our questions about ancient technology, but that they force us to ask those questions in the first place. They force us to confront the limits of our knowledge, the gaps in our understanding, the assumptions we have made about the past that may not be justified. The Baghdad Batteries are a challenge to historians, to scientists, to archaeologists, and to all of us who think we know how the story of human civilization unfolded. They are a crack in the edifice of conventional knowledge, a fissure through which we can glimpse a past that is stranger, richer, and more complex than we have imagined. We may never solve the mystery of the Baghdad Batteries. The evidence may simply be too fragmentary, too ambiguous, too distant to permit a definitive conclusion. The original artifacts may be lost. The craftsmen who made them are long dead. The world they inhabited has been buried under centuries of earth and rubble and history. But the questions remain, and questions, as we have said, are more valuable than answers, because questions keep us searching. Questions keep us thinking. Questions keep us humble. And questions keep us connected to the past, to the nameless men and women who lived and worked and wandered in the ancient land between the rivers 2,000 years ago, in a world that was both utterly different from ours and strangely, hauntingly familiar. Think of them. Think of the potter who shaped the clay, who sat at a wheel or pressed the earth between practiced hands, forming the familiar shape of a jar, a shape that had been made in this land for thousands of years. Think of the metalworker who rolled the copper sheet into a cylinder and soldered the seam with practiced skill, the smell of molten metal sharp in his nostrils, the heat of the forge warm on his face. Think of the craftsman who fitted the iron rod into the copper tube, who sealed the assembly with bitumen, who poured the acidic liquid into the jar and felt, for the first time or the 100th time, the tingle of the invisible force that flowed between the metals. What did he call it? Did he have a name for this force? Did he think of it as a spirit, a god, a demon, a natural phenomenon? Did he understand that it was the same force that made amber attract straw, that made the torpedo ray stun its prey, that made lightning split the sky? Or was it something entirely new to him, a phenomenon without precedent or explanation, a mystery that he accepted without understanding, as we all accept the mysteries of the world we inhabit? We will never know. The craftsman is silent. His world is gone. His knowledge, whatever it was, died with him or with the last person he taught. All that remains is the jar, the copper, the iron, the bitumen. All that remains is the device. And the device, when filled with vinegar and connected to a wire, still works, still produces voltage, still generates current, still does what it was designed to do 2,000 years after it was made. There is something profoundly moving about this, something that transcends the academic debate about electroplating and medical therapy and religious ritual. Something that connects us across the vast gulf of time and culture and language and experience to the person who made this thing. Because whoever he was, whatever he believed, whatever he understood or did not understand about the force he had harnessed, he was like us. He was curious, he was inventive, he was persistent. He looked at the world and he saw something that no one else had seen, and he built a device to capture it. That is the essence of the human spirit. That is the quality that has driven our species from the caves to the stars. That is the quality that built the pyramids and the Parthenon, that split the atom and decoded the genome, that sent ships across oceans and robots to distant planets. It is the quality of curiosity, of wonder, of the relentless desire to understand and to create. The Baghdad Batteries are a monument to that quality. They are small monuments, modest monuments, clay jars that fit in the palm of a hand. But they carry a message that is enormous. They tell us that the human spirit is older than we think, deeper than we know, and more resilient than we can imagine. They tell us that our ancestors were not the primitive, superstitious creatures we sometimes imagine them to be. They were scientists, they were engineers, they were innovators, they were in every way that matters, us. And what of the future of the Baghdad Battery research? What can we hope to learn, and how might we learn it? The most promising avenue of research is the continued application of modern analytical techniques to the original artifacts, if they can be located and made available for study. Advanced imaging techniques such as micro-CT scanning and neutron tomography could reveal the internal structure of the jars in unprecedented detail, showing the precise arrangement of the copper, iron, and bitumen components, and potentially revealing traces of the original electrolyte. Advanced chemical techniques such as mass spectrometry, isotope analysis, and residue analysis could identify the specific substances that were used in the jars, providing crucial clues about their intended purpose. Another promising avenue is the expanded archaeological survey of Parthian-era sites in Iraq and neighboring countries. The Parthian Empire covered a vast territory, and only a tiny fraction of that territory has been systematically excavated. If Baghdad Battery-like artifacts exist at other Parthian sites, their discovery could provide important contextual information about the distribution, use, and significance of the technology. In particular, the discovery of batteries in association with metalworking tools, medical instruments, or temple furnishings would go a long way toward resolving the debate about their purpose. A third avenue of research is the continued experimentation with Baghdad Battery replicas. While the basic capabilities of the design are well established, there is still much to learn about its performance under different conditions and with different materials. Systematic testing of a wide range of electrolytes, electrode materials, and operating conditions could reveal capabilities that have not yet been explored. In particular, experiments that test the battery's ability to produce specific effects, such as electroplating, electrolysis, or electrostimulation, under realistic ancient conditions could provide valuable insights into what the batteries could and could not have been used for. Finally, there is the avenue of textual research. The written records of ancient Mesopotamia are vast, spanning thousands of cuneiform tablets that have not yet been translated or published. Among these tablets may be references to the batteries, to the materials used in them, or to the processes they were used for. The discovery of such a reference, however oblique or coded, could transform our understanding of the Baghdad batteries and their place in ancient technology. The research continues, the mystery endures, and the Baghdad batteries, silent witnesses to a forgotten chapter of human ingenuity, wait patiently for the day when their secrets will be revealed. But perhaps the most important thing the Baghdad batteries teach us is not about the past. It is about the present. It is about how we think about knowledge, about progress, about the relationship between what we know and what we assume. We live in a world that is saturated with technology. We carry computers in our pockets, communicate instantaneously across continents, travel through the air at hundreds of miles per hour, and probe the deepest structures of matter and the farthest reaches of space. We are, by any measure, the most technologically advanced civilization in human history, and we are proud of that achievement, as we should be. But the Baghdad batteries remind us that our achievement is not as unique as we think. They remind us that other civilizations, in other times and other places, also achieved remarkable things, things that we did not expect, things that we cannot fully explain, things that challenge our assumption that we are the first and only people to have understood the forces of nature. They remind us that knowledge is not a possession. It is a process. It is not something we have. It is something we do. And if we stop doing it, if we stop asking questions, stop testing hypotheses, stop challenging our assumptions, stop teaching what we know to those who come after us, then our knowledge, like the knowledge of the Parthian craftsmen, will be lost. It will be buried in the earth, forgotten, waiting for some future civilization to dig it up and wonder at it. The Baghdad batteries are a warning as much as they are a wonder. They warn us that progress is not inevitable, that knowledge can be forgotten, that civilizations can decline and fall, taking their achievements with them. They warn us that the arc of history does not always bend toward advancement, that there are dark ages as well as golden ages, that the light of understanding can go out as easily as it was lit, but they are also a source of hope. Because if a Parthian craftsman, working 2,000 years ago with nothing more than clay, copper, iron, and vinegar, could discover the principles of electrochemistry and build a working battery, then the human capacity for innovation is even greater than we imagine. It is not limited to the laboratories of the modern world. It is not dependent on computers, textbooks, or formal education. It is a fundamental property of the human mind, as natural and as universal as the desire to eat, to sleep, to love, and to understand. The Baghdad Batteries tell us that we have always been scientists, we have always been engineers, we have always been seekers of knowledge and builders of tools. We have always looked at the world and asked, how does this work? And we have always, in our own way, in our own time, with our own materials and our own understanding, found answers. Some of those answers were lost, some of them are being rediscovered, and some of them perhaps are still waiting to be found, buried in the earth of ancient lands, hidden in the cryptic texts of forgotten languages, preserved in the silent artifacts of civilizations that flourished and fell and left behind only the faintest traces of what they knew. The Baghdad Batteries are one of those traces. They are a message in a bottle, tossed into the sea of time by an unknown hand, washed ashore on the beach of the present, and waiting to be read by anyone with the curiosity and the courage to try. 2,000 years ago, in the land between the rivers, someone held lightning in a clay jar. They did not call it lightning. They did not understand it as we understand it. They did not know about electrons or ions or electromagnetic fields. They did not know that what they held in their hands would one day power cities, drive machines, illuminate the darkness, and connect the world in ways they could not have imagined. They knew only that it worked, that when copper and iron were placed in vinegar, something happened, something invisible, something powerful, something that tingled on the skin and coated one metal with the shimmer of another, something that made the impossible possible and the ordinary extraordinary. They held it in their hands. They studied it, they used it, they built devices to exploit it. And then, for reasons we cannot know, they set it down. They sealed the last jar, laid it on a shelf, and walked away. And the world forgot until now. The Baghdad Batteries are not just artifacts. They are not just curiosities in a museum display case. They are proof that the human mind has always been reaching, always exploring, always seeking to understand the world and to bend it to human purposes. They are proof that the story of technology is not a straight line from primitive to advanced, but a complex, branching, often broken path, full of detours and dead ends and unexpected discoveries. They are proof that we are not the first to wonder about the forces of nature, and we will not be the last, and they are a challenge. A challenge to look at the past with new eyes, to question what we think we know, to remain open to the possibility that the ancient world was richer and more complex than our textbooks suggest. A challenge to protect the knowledge we have, to share it widely, to transmit it faithfully, and to never take for granted the fragile chain of understanding that connects us to our ancestors and to our descendants. The clay jars are silent now. The copper is green with age. The iron is consumed by rust. The bitumen is cracked and dry. The vinegar or wine or whatever liquid once filled these vessels evaporated centuries ago, leaving behind only faint chemical traces on the walls of the jars. But the questions they raise are alive. The mysteries they embody are unsolved. And the story they tell, the story of human ingenuity, human curiosity, and human loss, is as relevant today as it was 2,000 years ago, when a craftsman in ancient Mesopotamia first felt the tingle of an invisible force and knew, without knowing why, that he had discovered something important. Something that the world would forget, and something that the world eventually would remember. The Baghdad Batteries, ancient electricity, 2,000 years of silence. And a mystery that may never be fully solved, but that will never, ever stop being asked. The earth holds its secrets loosely. It gives them up sometimes to shovels and trowels and the patient hands of those who dig. It gave up the Baghdad Batteries in the 1930s to construction workers who did not know what they had found. It gave up the Dead Sea Scrolls in the 1940s to a shepherd boy chasing a goat. It gave up the terracotta army in the 1970s to farmers digging a well. The earth is generous with its gifts, but it does not explain them. It gives us the artifacts, the objects, the physical remains of the past, but it does not give us the context, the meaning, the intention behind those objects. That we must supply ourselves through the patient, imperfect, endlessly fascinating work of interpretation. The Baghdad Batteries have been interpreted in many ways, as batteries. As scroll jars, as ritual objects, as medical devices, as tools for electroplating, as instruments of religious deception, as evidence of lost super-civilizations, as products of overactive imaginations. Each interpretation reflects the assumptions, the knowledge, and the limitations of the interpreter as much as it reflects the nature of the artifacts themselves. And perhaps that is the final lesson of the Baghdad Batteries. That the past is not a fixed thing, not a static collection of facts waiting to be discovered. The past is a living thing, a dynamic interaction between the evidence that survives and the minds that interpret it. It changes as we change. It grows as we grow. It reveals new facets of itself as we develop new tools and new perspectives for examining it. The Baghdad Batteries meant one thing to König in 1938. They meant another thing to Gray in 1940. They meant another thing to Eggebrecht in the 1970s. They mean something different to the researchers of today, who bring to them the tools and the questions of the 21st century. And they will mean something different to the researchers of the future, who will bring to them tools and questions that we cannot yet imagine. The mystery of the Baghdad Batteries is not a mystery that will be solved once and for all. It is a mystery that will be revisited, re-examined, and reinterpreted by each generation that encounters it. And each generation will find in these simple clay jars something that speaks to its own concerns, its own curiosities, its own understanding of the world. That is the power of a great mystery. It does not end, it does not resolve. It does not yield a single definitive answer that closes the book and settles the question. It endures, it challenges, it inspires. It connects us across the centuries to the people who came before us and to the questions that will outlive us all. The Baghdad Batteries are such a mystery. And they will remain so long after we are gone, long after our civilization has risen and fallen and been buried in its turn, long after some future digger breaks through the earth and finds the remnants of our world and wonders, as we wonder now what we knew and what we forgot and what we might have discovered if we had only had a little more time. 2,000 years ago, someone in the ancient land of Mesopotamia discovered electricity. We know this because they left behind the evidence, sealed in clay and buried in the earth, waiting for us to find it. We have found it, we have tested it, we have debated it, and we are still, after all these years, trying to understand it. The Baghdad Batteries, a mystery from the ancient world, a challenge to the modern mind, and a testament eternal and enduring to the boundless curiosity of the human spirit. The jars are silent, but the questions they ask will echo through the ages. And as long as there are minds to ask those questions, as long as there are hands to dig in the earth and eyes to see what the earth reveals, the story of the Baghdad Batteries will continue. It is not over, it has barely begun. This concludes our documentary on the Baghdad Batteries. The clay jars of ancient Mesopotamia, small enough to hold in one hand, have opened a window onto a past that is deeper, stranger, and more wondrous than we ever imagined. Whether they were batteries, ritual vessels, medical devices, or something we have not yet conceived, they remind us of a truth that is as old as humanity itself. We have always been seekers, we have always been builders, we have always reached for the unknown, and sometimes in the most unexpected places, in a handful of clay and copper and iron, we find evidence that our reach extends far further back into time than we ever dared to believe. The mystery endures, the search continues. And the past, as always, has more to tell us than we are yet prepared to hear.